Let's begin our session. Session estimation and filtering methods for fault diagnosis. Chairs of session Lopez Estrada, Francisco Ronay, and co-chair Cengiz Hacıyev. We have 6 presentations in our session. The first one, title of estimation, is a kernel-based approach to data-driven actuator fault estimation. The authors, Sheikh Muhammad Amin, Muhajirin, Peyman, and Thomas, will be presented by Amin. Please.
So, good morning, everyone. Thank you all for joining this session. Thank you all for joining this session. I'm a PhD student at TU Delft in Delft Center for Systems and Control. Together with my supervisory team, Peyman, Muhajirin, Esfahani, and Tomasz Kiewicki, I'm going to present the work on kernel-based method for data-driven fault estimation. So at first, I'm going to give a brief background and introduction about the problem, what class of the problem that we are interested in, and then I'm going to show how we formulate the problem. So any real-life application includes these groups of input-output signals, which these signals in this picture comprises the all natural disturbances that present in the dynamical system. But on top of these signals, what we are interested in is the fault signal, is external fault signal, that the main goal is to design a filter to estimate the fault. What we mean by that is that if the fault is changing over the time, the main goal is to design a filter that tracks the change in the fault. And we call this class of the problem as the fault estimation or reconstruction in the literature, which is the most difficult class of the problem in fault diagnosis, because we are not only interested in detection and isolation, but also we want to track the changes in the fault. And who is going to use the result of the paper that we actually wrote is that the people who are dealing with the fault and control, predictive maintenance, perfect tracking system, they can all use the result here. So then I'm going to show what kind of the setup and framework that we used for this problem. If we show the system, the linear dynamical system in a most general form in STT-based representation, what makes the problem non-trivial and is that what kind of the challenging that we have in this problem to deal with. The first one is that I don't have any access to the system parameters, which makes the problem data-driven. And the second part is that I'm not making any assumption on how the fault going to change with respect to the time. So there is no pattern. I'm not considering any pattern for the fault. And another one is that the underlying fault subsystem might include some transmission zeros. As we know from the systems and controls, there might be a pair of the initial condition and input that makes the output of the system to the zero. So in that case, there is no way and impossible to reconstruct the input. And this makes problem more challenging. And among these transmission zeros, I'm also saying that some of them might include the non-minimum phase zeros. And as we know, the non-minimum phase zeros makes the inverse of the system and the filter that we are designing in a classical way unbounded or growing exponentially. So what I need to, so in that setting, it's kind of a well-posed problem. Sorry, it's an ill-posed problem because I don't have the system parameters, I don't know the fault, and I don't know how the fault is going to impact the system. So then I need to make some assumption to make the problem solvable or well-posed. The least assumption that I'm going to make is that I have access to the healthy or normal trajectory of input-output data. And second one is that I'm saying that the type of the fault that I'm interested in this problem is additive. Then what I'm going to highlight here is that at the heart of any type of reconstruction methods, like here fault estimation, we are dealing with the problem of system inversion. And why I'm saying that it's a system inversion? Because in the classical way of doing the fault estimation, the filter is going to be of 2 elements. The first step is going to, we actually generate the residual signal and then trying to inverse the underlying fault subsystem to reconstruct the fault. So all important here is that we need to have the inverse of the fault subsystem. And this is why I'm saying that this is a system inversion problem in general. And the more precise we have the inverse of this fault subsystem, the more accurate would be the estimation, the fault estimation. And then if I want to compare the method that we proposed in this work to the state-of-the-art methods in the literature, on the left-hand side, you see that let's say the state-of-the-art suggests that for the fault estimation, we need to follow 2 steps. In the first part, we do the identification steps, and then this will be followed by the inversion operation to provide the fault estimation. But there are 2 main issues with the current solution. The first one is that, as you see here, in the first step, we are making some identification error, and this is going to non-linearly propagate to the fault estimation. And the second one, which is more important for the sake of this talk today, is that the optimization we are solving in the current method, in the first step, is not optimized for being used as the inverse. So we have no idea what the inverse of the identified model look like after inversion operation. Instead, we are suggesting to directly estimate and identify the inverse of the system. And what we get by doing that is the first one is that the optimization that purports for the direct method is going to be used for the fault estimation goal. And the second one is that the fault estimation error is going to linearly depend on the identification error. Then how we are going to solve this problem? The fault-free system or the healthy system in the most general linear form can be represented by this VARX model or input-output model with the help of the subspace identification, where the A and B function includes the Markov parameter corresponding to the input-output signal. Then I can construct the inverse system from the output to the input by manipulating the coefficient, where the main change here is that instead of the A governing the dynamics of the original system, in the inverse system, I'm dealing with the B, with the coefficient related to the input signal, where the transmission zeros is actually living into that. So then, as I mentioned before, the presence of the non-minimum phase zeros makes the problem challenging, why the inverse of the system is going to be unstable or unbounded. So this is the bad news, but the good news is that under certain conditions that I can represent the causal unstable behavior with a mixed causal non-causal representation, where the main requirement that I need to kind of have this kind of mixed causal non-causal representation is the system shouldn't have any zeros on the unit circle. And if I can meet this criteria, then I can represent the inverse of the system in a bilateral representation, where actually the inverse of the system comprises of 2 elements. The first part can accept actually the negative integer for the time. This is why I'm saying it's a non-causal representation. That means I need to have access to the future data. And the second part is actually the historical data. And then now I can actually, so up to that, I presenting the input-output model for the inverse system by making the convolution of the output signal with the bilateral Markov parameters. And then, since the fault is additive in this problem, I can subtract the input signal that I have access to provide the estimation for the fault. So the main goal in the training phase is to find this map from the healthy trajectory to this bilateral Markov parameters. And the first thing that we do for making and identifying this Markov parameter is to solve the optimization problem, where the typical choice is for the typical choice is to minimize the square norm of the error. But there are 2 shortcomings with the original optimization problem, where if you see here that this bilateral representation needs infinite number of the Markov parameters to represent the exact inverse of the system, which I'm going to call this part requires the future data, which is a preview time that we need for this solution, which is we don't have access to in practice. And the second one is that, so the problem is, in general, is the infinite dimensional. So we cannot have a parametric model. So it's going to lead to the non-parametric. So what kind of solution that we might have here is the first one to truncate the model, at least admit some kind of the estimation error, but at least we can solve the optimization. But the second one, which is more a smart way to handle the problem, is that without sacrificing the performance, we might introduce some regularization, a specific regularization to handle this infinite dimensional optimization problem, which is the case here. So now I'm going to introduce another optimization problem, including the regularization of the reproducing kernel Hilbert space, where this additional term that you see here, asking the problem to instead of searching the whole space of the parameters Rn, just limit themselves to the hypothesis space or function space, which is characterized by this reproducing kernel Hilbert space. And the information that, additional information that I'm using in this regularization is this extra information here, which we could call as a prior. And if this space have certain properties I'm mentioning here, then I can solve the problem effectively. And the good thing about this optimization problem is that I can directly enforce a desired behavior into the inverse of the system, including a stability that was an issue in the less typical solution in the state-of-the-art method. Then, as I said, if the space that I'm using at the time looking to search for the parameter is RKHS, then by using this theorem, representative theorem, that I can show that this infinite dimensional problem can admit a finite solution. That means the function that I'm going to estimate can be represented by the linear combination of the basis function or the kernels that actually construct this space for me. Then what kind of kernels I'm going to use in this solution is, as I mentioned, that the dynamics of the inverse system is going to be governed by the zeros of the original system. So the type of the kernel that I'm using is a non-causal rational orthonormal basis function, which is a cascade of the all-pass transfer function, which is initialized as a hyperparameter with some poles, which this pole is nothing but the knowledge that we might have on the zeros, location of the zeros of the original system. And then I can construct the kernel matrix, but look here that this is a non-causal representation. That means the time index here also admits the negative integer. And what is the motivation of using this basis is that each of them can have the infinite impulse response. That means the slow dynamics can be captured effectively by the relatively low-order model. And then if I want to, in a nutshell, introduce the framework, putting all the blocks together, in the first phase, in the offline phase, we need to construct the kernel matrix, which is parameterized by these generating poles, and using the healthy trajectory to solve the optimization problem and coming up with the bilateral marker parameters. And then in the real time, what I need only is the input-output real-time operational data to perform the false estimation based on the inverse system-based proposed filter. Then in the first simulation result, I want to show that for a system that has some zeros, some transmission zeros really close to the unit circle, we know that the more closer the zeros to the unit circles, that means the more number of the coefficient that we need to represent the system. So this is a really challenging case that shows that the zeros are actually really close to the unit circle, but however, by using this optimization problem, we can effectively capture the, let's say, correct behavior of the inverse system. And this is a bilateral representation. But in the main, let's say, performance for the false estimation problem, we are performing the Monte Carlo simulation to verify the result on the validation data, where in the left-hand side, actually, the color are not representing here correctly. But this is the yellow color, so this is the method that we proposed here, and this shows the estimation error. But the state-of-the-art, which was the indirect method, including 2 steps, obviously providing a biased estimation. And if I want to show for one specific realization of the, let's say, stochastic part, the noise signal, this is the type of the scenario that I'm challenging the problem, challenging the method, which the false signal is the combination of the sinusoidal signal together with the step function. And the red one is actually the proposed method, And the blue and the green is the state of the art, which is the receding horizon fault estimation, which was the state of the art. So here, the fault is going to be non-zero at this point. And the method that we propose, providing the estimation for the fault after really a small delay, but compared to the state of the art, if we want to have, let's say, acceptable performance of the state of the art, we need to make that much delay to provide the estimation for the fault. And the filter order that you use in the proposed method is here is a 60, let's say. But let's say, state of the art, we need at least more than twice the, let's say, proposed filter. And what more that I want to mention here is that if you recall, when I was comparing the indirect method with the, let's say, direct method, I was saying that if I use the true Markov parameters, that I'm not making any kind of identification error. In this case, still, I might not perform as best as the proposed method. And then, as a conclusion, what we did differently in this let's say, proposed work is that, so we exclude actually the inversion step in the, let's say, typical solution for the fault estimation and propose the optimization problem, which is just used for the fault estimation goal. And then we solve the instability issue at the design stage and using the non-causal kernels. And on the performance, we provide the more accurate estimation for the fault. And at the same time, we use the low-order filter to do so. And that means we make, let's say, less estimation delay. And what's coming next is that we show when actually the direct method is going to outperform the indirect methods, which would be the, let's say, follow-up work on this result. And as a takeaway here, what I want you actually to remember is that using the mix of the optimization with the inversion is not always the best solution. Thanks all.
Thank you for presentation. Have you any questions to the presenter? I have one. What type of faults are taken into consideration?
What type of faults?
Yeah.
So as I mentioned, as I mentioned, maybe in the, let's say, introduction part, the type of the fault that I'm interested is the additive fault, actuator additive fault, yes. Not the, let's say, multiplicative, because that could be more challenging to solve, but in this stage, let's say, at least the least assumption that I can make to at least solve the problem is that I'm assuming that the fault is going to impact the system in additive way. Yes.
More questions?
Yes. Hi. Thank you for your interesting presentation. One question. Is this...
Thank you very much.
Sorry. Yeah. Yeah. Quick question. Like, how easy is for this method to be extended to nonlinear systems? Because in the beginning, I thought you presented a linear.
As I said, that this is the most difficult class of the problem in fault. So I'm going to do the data-driven stuff, and I'm not making any assumption on the fault. So let's say the very basic or simple that at least I can handle the problem is the linear cases. But if I want to extend the result for the nonlinear one, so I'm going to use the input-output model for representation. So instead of using this bilateral Markov parameters, I can actually use, let's say, another type of the nonlinear system, nonlinear, let's say, polynomials function that can represent the system, which is linear in the parameter, even though that the representation might be nonlinear. So there is a chance actually to extend also the result here for the nonlinear cases.
But for a specific subclass that it's still linear to the parameters?
Yeah, for sure for a class of nonlinear systems, not okay. General one, yes.
Nice.
That's true.
Thank you very much.
Great.
The second presentation. It's a video presentation.
Yes.
Yeah. The title of presentation: Distributional Robust Approach to Active Fault Detection for Linear Stochastic Dynamic Systems by Ting, Jardong, Lan Lin, Li, and Zhong Ping. the video presentation.
Hello, everyone. Good morning. And due to some reasons, the first author of this presentation, Dr. Xue, didn't come to the beautiful photograph for our meeting. Fortunately, she prepared a video presentation for everyone to watch. If you have any questions, you can send her email for communication. Thank you very much.
Good morning, everyone. I'm Ting Xue from Shanghai Maritime University in China. I'm pleased to introduce our work in this session, and sorry that I'm unable to attend the live meeting. If any questions and comments, welcome to contact with me through this email. The topic of the presentation is about applying a distributionally robust approach to cope with active fault detection issues for linear stochastic dynamic systems. It's a cooperation work with Professor Dong Zhao from Beihang University, Professor Li Linlin from Beijing University of Science and Technology, Professor Li Yueyang from University of Jinan, and Professor Zhou Maiying from Shandong University of Science and Technology in China. I'm going to give this talk in 4 parts. Firstly, the motivations will be briefly introduced. Then the problem to be addressed is formulated, and some preliminaries are revealed. After that, a solution based on distributionally robust optimization is presented, followed by conclusion. Now let's start with the motivations. As we all know, over the past few decades, tremendous achievements on model-based fault detection have been obtained. Among the results, one mainstream technology is passive fault detection, the key idea of which is generating a so-called residue signal by means of methods such as observers, parentage relations, and parameter estimations, and so on. In comparison, active fault detection provides a powerful tool to deal with multiplicative fault detection issues, the key of which lies in designing an appropriate auxiliary signal so that possible abnormal behaviors of the system can be separated from the normal mode before the end of the testing period. Moreover, according to the monitored system subjected to either deterministic or stochastic disturbances, active fault detection approaches can be roughly classified into the deterministic methods and stochastic methods. In deterministic active fault detection, additive disturbances are generally considered to be non-bounded or energy-bounded. The input-output observations thus can be described with closed sites, both for fault-free and faulty cases. An auxiliary signal is then designed towards separating these two sites completely. That means the intersection of omega 0 and omega 1 is empty. In the framework of stochastic active fault detection, statistical analysis and probability theory are widely applied for auxiliary signal design, especially when the probability distribution for stochastic disturbance is known, for example, Gaussian distributed noises. Bayesian theory, KL divisions, and Mahalanobis distance are generally used to active fault detection system design. However, in practical applications, precious probability distribution for disturbance is inaccessible. In this case, how to design an active fault detection system remains an active and open topic. Motivated by these concerns, we developed a new active fault detection method by using distributionally robust optimization technique. To introduce clearly, a description of the monitored system and some preliminaries are first given. Consider a stochastic linear discrete time invariant system in equation 1, where Gi with I equals to 0 denotes a system in 4 free keys. G1 for I equals to 1 denotes a system subjected to multiplicative fault. Here xi is the state vector, y is the system output, and u is the auxiliary input to be designed. System matrix AI, BI, CI, DI, EI, and FI are known for system G0 and G1. The relationship of these matrices are modeled as seen in equation 2. Here, delta F reference represents a reference for multiplicative faults under consideration. In general, for fault detection purpose, an observer-based residual generator can be constructed and seen in equation 3. Here, L denotes the observer gain matrix that symbolizes A minus LC. R is a residual signal. Furthermore, the dynamics of the residual generator can be obtained and seen in equation 4, which builds the relationship between residual signal R, auxiliary input U, and the disturbance Di. Despite the unknown exact probability distribution for disturbance Di and the augmented initial state tilde x0, we can without loss of generality assume their converse matrices are known. In residual evaluation stage, an evaluation function g of r and a threshold gth are determined such that the occurrence of a fault can be detected by performing this decision logic. Here, w and b represent the parameters to be determined. Hence, the design of an active fault detection system lies in the design of auxiliary input U, the parameters W and B. Now we come to the problem formulation. We know that false alarm rate and fault detection rate or misdetection rate are usually applied to evaluate the fault detection accuracy in the probabilistic context. False alarm rate is the probability of the residual evaluation function larger than the threshold in 4 free keys, and the misdetection rate is the probability of residual evaluation function smaller than the threshold in 40 keys. It's noted that due to the unknown exact probability distribution for initial state and stochastic disturbance, it's difficult to compute the exact value of false alarm rate and misdetection rate in the probabilistic context. An alternative way is to mirror the upper bounds of false alarm rate and misdetection rate in the worst case setting, just like this. Meanwhile, the injection of an auxiliary input into the system shouldn't influence the system dynamics seriously. Thus, the energy of the auxiliary input over testing period shouldn't too large, so it should be as small as possible. Therefore, towards achieving satisfactory fault detection performance, the design of the auxiliary input U evaluator parameters W and B can be formulated in this problem, where the parameters alpha and beta represent the predefined upper bounds of false alarm rate and misdetection rate respectively. Okay, we can see that the key of solving this problem lies in addressing the last two probabilistic conditions. Under consideration of unknown exact probability distribution for disturbances, we will develop a distributionally robust solution to the above optimization problem. To this end, An input and output model of the residual generator over finite time horizon can be obtained and seen in equation 6. Here, n is the length of the time window. Matrix HUI and HDXI are related to the system matrix and the observer gain matrix. It's remarkable that the disturbance DIN is stochastic and its probability distribution is unknown. Well, the disturbance is unknown, but its zero mean and its converse matrix is available. Then we can introduce a new stochastic variable Ci, which is zero mean and having identity converse matrix. Then the residue can be rewritten as in this form. It means and a converse matrix in for free and 40 case can then be obtained like this. Despite the unknown exact probability distribution for residue, we can, without loss of generality, construct the mean kernel-based ambiguity sites P0 and P1 in for free and 40 cases to characterize the residue, respectively. In this sense, the conditions related to false alarm rate and method detection rate can be converted into two distributionally robust chance concentrates in equation 7. To handle these two diseases, theorem 1 is recorded. It shows that for any probability distribution belonging to the ambiguity site P with identity mean and converse matrix, such a DCC condition can be equally converted into a deterministic condition of this form. Here, omega Xi epsilon is a convex set, and the upper bounds of this Mahalanobis distance is related to the probability upper bound epsilon. Based on theorem 1, the original diseases can be represented as two deterministic conditions of this form. The non-bounded size of residue in for free and 40 cases are related to the false alarm rate upper bound alpha and the method detection rate upper bound beta. Obviously, if we can find a hyperplane to separate these two sites, omega R0 alpha and omega Rn1 beta, then the upper bounds of false alarm rate and method detection rate for any probability distribution belonging to ambiguity site P0 in for free case and PRN belonging to the ambiguity site P1 in 40 case can be guaranteed not larger than alpha and beta, respectively. In this context, the original probabilistic optimization problem can be equally converted into this deterministic optimization problem. Now we are in the position of solving the above deterministic optimization problem. The results in reference 2 can be applied to this aim, and an analytical solution is given in theorem 2. Just see this equation, the core of which lies in solving a generalized eigenvalue-eigenvector problem, and the optimal hyperplane can also be determined with respect to W and B. Up to now, without exact probability distribution for disturbance, an active fault detection system integrated with false alarm rate and method detection rate performance indexes have been developed in the probabilistic context. And the summary, in this study we have developed a new auxiliary input design method in the distributionally robust optimization context. Performance indexes, false alarm rate and method detection rate have been integrated into the active fault detection system design, and the developed active fault detection system is robust against the distributional uncertainties of disturbance. This work also presents a possible connection between stochastic active fault detection and deterministic active fault detection. These are some references. Thank you very much for your attention and valuable time.
Thank you for presentation. Have any questions to presenter? I have one. Is your observer is deterministic or stochastic?
Questionnaire is used for, you have to send the question for email because it's a video presentation.
I don't understand.
You have to send the question by email.
Ah, yeah. Thank you. No questions? Thank you.
Okay, I will take it from here. We're going to continue with the next presentation, constraining multi-output Gaussian process regression for data reconciliation. Okay.
Okay, good morning, everyone. Thanks for the opportunity to present to you today on the work done by myself, Professor Tuabilo, and Stephen Bradshaw, all of us at the Department of Process Engineering at Stellenbosch University, South Africa. On the development of a constrained multi-output Gaussian process regression model for data reconciliation. So just a very brief background. As we all know, industrial processes have inaccuracies in measurements, such as excessive noise, faults, or sampling rate mismatch, which is detrimental to performance. And so we apply process monitoring, which aims at detecting faults to improve the data quality. And this is to ensure the safe, efficient, and profitable operation. In sensor validation, we look at fault detection and diagnosis, but more importantly for this talk is the final step of reconstruction of the faulty value using knowledge on physical laws. So one way of doing value reconstruction is data reconciliation. This is a not data-driven model. This is a model-driven approach that exploits redundancy, both sensor redundancy and analytical redundancy, to reconcile measurements to adhere to physical constraints. These physical constraints come from conservation laws, so mass, energy, and momentum conservation. We have two approaches for this, steady state and dynamic data reconciliation. In the steady state case, this is normally applied to normal operating conditions. These models have very high confidence, but they have limited applications typically. Furthermore, we only apply steady state data reconciliation at discrete time points. On the other hand, we have dynamic data reconciliation, such as the Kalman filter, which has been used for this. This requires the use of a dynamic process model, exploits further temporal redundancies, but typically for large industrial processes, the development of a dynamic model can be very costly, difficult, or even impossible. And they also suffer from plant model mismatch. And so in cases where we have very poor data quality, or we don't have high model confidence with our dynamic models, typically we prefer to use steady state data reconciliation. And this is often the case in minerals processing industry. Just a brief theory on steady state data reconciliation. It involves solving a constraint optimization problem. So in this case, we have a measurement y, and we seek to find a y hat, the reconciled estimate that minimizes an objective function, subject to the constraint g of y equals 0. For linear constraints, our constraint equation simplifies to a plane in our measurement space, where matrix M denotes an incidence matrix. In this case, if we draw a boundary around the system we are performing our conservation constraints on, the incidence matrix will have a value of 1 for inlet flow rates or inlets to the system, -1 for outlets, and 0 otherwise. Moving on to some theory for Gaussian process regression. Gaussian process regression has seen in the past 10 or so years an increase in use for process monitoring applications, specifically fault detection or MPC for safety critical systems. GPR is a data-driven stochastic process which describes a set of random variables, any collection of which is normally distributed. And so a property of the Gaussian process is that it is fully specified by its mean function, mx, and the covariance function, k, which is supplied by the user. The selection of the covariance function determines the behavior of the Gaussian process, and typically one we like to use is the exponentiated quadratic covariance function. This comes with a smoothness assumption. And this is in the Bayesian framework, this is our prior assumption. But more useful is to perform Gaussian process regression, where typically we assume we have some latent process corrupted by noise, and we only observe why the noise corrupted measurements. And so if we look at the prior distribution at the top right there, our Gaussian process will give us a mean and some estimation of the variance, the prediction variance. But what we're interested in is the conditional distribution of our Gaussian process output conditioned on noisy measurements. And by using the squared exponential covariance function, this is a normal distribution with a very well-defined mean and covariance. And for the case, or for the sake of this work, what we would like to do is to use, or see if we can use Gaussian process regression to solve the data reconciliation problem. So what I've shown now was the single output Gaussian process regression case, but it can also be extended to multi-output Gaussian process regression. So in this case, the joint probability distribution of two separate or two outputs will also be a normal distribution. So for functions 1, f1, and f2, each will have its own covariance function. And if we take those cross-covariance terms as 0, this is equivalent to performing single output Gaussian process regression. A bit more useful is to model those cross-covariance terms explicitly, which we can do through multi-output Gaussian process regression. One such model is the semi-parametric latent factor model, where we model, we have latent Gaussian processes U1, U2, up to UQ, which we then can take a linear combination of to get output functions, as many as we need. So each output function, f sub d, is a linear combination of our latent functions. And the property here, which is quite nice, is that the covariance function, those cross-covariance terms, have a very, as an analytical solution. And so hopefully now we are in a better position to try and, not reconcile, but combine these two approaches to get to our goal of performing steady-state data reconciliation with Gaussian process regression. Just taking a step back to the steady-state DR problem is that there's an equivalent method of solving the problem. Instead of getting a set of reconciled measurements that adhere to our constraints, alternatively, we can try to find a vector U, which is in the latent space, which can then be projected via matrix A0 into our measurement space Y. Here, the plane is then spanned by the columns of matrix A0, which is found in the null space of our incidence matrix. As I've mentioned, steady-state data reconciliation is only applied at discrete time points. But for our purposes, what we would like to do is to alternatively model the latent function U using Gaussian processes. For the semi-parametric latent factor model, typically those linear combination factors A would have to be found as an additional parameter. But now we are combining the approach where the semi-parametric latent factor model gives us the covariance matrix, where the steady-state data reconciliation gives us the linear combination factors A. And so we now have a physical interpretation for those constants. Since we start at the latent space U and project that back into the measurement space, our Gaussian process, or multi-output Gaussian process, will physically adhere to the constraints. And we now get to use some of the benefits of using this Bayesian model, which is robust to missing data or sampling rate mismatch. And as a stochastic model, it provides us with a prediction posterior distribution instead of just single point estimates. As an illustrative case study, we applied this to a blending tank case study just to see how the model performs in different scenarios. And so we've chosen to compare the steady-state data reconciliation model with single output Gaussian process regression and our constrained multi-output Gaussian process regression model. In this case, we have a blending tank with 2 inlet streams, 1 outlet stream, and measurement redundancy. We introduced 4 different scenarios. The first one is normal operating conditions. Then to reduce the sampling rate of flow rate 3 to introduce sampling rate mismatch, to introduce a precision degradation fault in F3, and finally to do, even though we've used a steady state model, to see how this model will perform if we do introduce dynamics. So for the first case, these graphs are quite messy, but bear with me. The solid black line is our ground truth, from which we have generated the noisy measurements by the black axis, and then we applied the 3 different models. So steady-state data reconciliation is the circles, single output Gaussian process regression is the blue line with the credibility interval, and the constrained multi-output Gaussian process regression in the red. In the steady state, or in the normal operating conditions case, we see that the Gaussian process regression-based models both are able to approximate the latent or the ground truth quite accurately, with a quite low root mean squared error shown in the right. Whereas we have the characteristic performance of the steady state data reconciliation where we have these decorrelated estimates. When we reduce the sampling rate of flow rate number 3, we introduce sampling rate mismatch. And we see that still both the Gaussian process regression-based models still perform quite well, whereas there's a slight increase in the uncertainty interval for the steady state of the single output Gaussian process regression model. The steady state data reconciliation model performs quite well still. However, it should be noted again that we had to introduce, we had to do linear interpolation where a complete set of measurements was not available as an additional step, whereas with the Gaussian process-based models, this is inherently done by the model. Perhaps a bit more interesting is introducing a sensor fault where we have precision degradation halfway through the simulation. In these cases, again, we see that the Gaussian process regression-based models perform quite well, approximate the ground truth, whereas our steady-state data reconciliation now starts to fail. We can calculate using the probability distribution or the predictive distribution by the Gaussian process models to calculate the negative log likelihood, where we see where the sensor fault is introduced, there's quite an increase in the negative log likelihood. And so for future work, we think that this might be useful for fault detection applications. And then finally is the introduction of process perturbations. So even though we have based this on a steady state model, it could still be useful to evaluate what would happen if these models are applied to dynamic systems. So in this case, we've introduced step changes in our inlets and then applied the models to the resulting responses. And so here we see that the Gaussian process-based models both starts to fail. And this is likely due to the implicit smoothness assumption in the choice of covariance function, which is now being violated during step changes. So in conclusion, the past few years of literature show that there is a scope for applying Gaussian process regression to process monitoring. And in the current work, we try to do or try to develop a constrained Gaussian process regression model which incorporates constraint conservation laws. As a Bayesian model, we get some benefits such as it handling unequal sampling rates or giving a predictive posterior. From the results, we see that the Gaussian process-based models are able to perform well with normal operating conditions, unequal sampling rates, or precision degradation, but they do fail when dynamics are introduced. For the future, the steady state or the linear steady state model is quite restrictive, so we would like to extend this to the bilinear case, which is a special subcase of nonlinear systems. For example, with a chemical engineering application is to find both a flow rate and a composition and reconcile those simultaneously. Second, that I've not mentioned is the high computational cost of using Gaussian process regression, since this involves the inversion of an n by n matrix, where n is the size of the data set, and that scales with O(n) cubed. So this makes GPR quite difficult for large data sets, and it would require the use of sparse approximation techniques for large data sets. And finally is to assess the performance of this or develop this further for fault detection applications. Thank you.
Okay, we have time for questions. Any question? I had a small question. You test this approach with this small system, no? With this process system. Did you try with other more complex systems?
For this initial investigation, we first tried to do simple systems so as not to introduce unnecessary complexity. But the next step would be to do more complex systems and even apply it to industrial case study.
If the system is more complex, the computational cost is also higher, no?
Yes, because you will have more training data, and that requires the inversion of quite a large matrix, which is computationally expensive. Okay. So for those cases, you would need to resort to sparse approximation techniques.
It will be a good challenge, no? For mechatronic system especially. Okay, thank you very much. We have again. Okay, we're going to continue with the next presentation. It is spectral conditioning within the energy graph-based visualization for detection method.
Hello, everyone. Thank you for joining this presentation today. I'm Vikas Vormerans, and my co-authors are George van Schoor and Kenneth Uren, and I will be presenting today on spectral conditioning within the energy graph-based visualization fault detection method. So just for a presentation outline, I'll start off with an introduction and a general problem statement, and then I'll give you a quick overview of the practical process that we considered for this study. Then I'll tell you a bit more about the energy graph-based visualization algorithm. And then we'll move on to the specific problem statement, which is which will then be solved by using the the sample self-comparison method and the hybrid sample self-comparison method. And then we'll have a comparison of results, and then finally a conclusion and some recommendations. Okay, so as an introduction and a general problem statement, if we consider general process operations today, there are typically 3 process drivers for industrial plants, which is safety, production output, and environmental compliance. And these 3 drivers tend to increase constantly. Environmental compliance and regulations become stricter, safety requirements become stricter, and production outputs tends to increase year on year. And so this ironically leads to more process complexity because we need to upgrade the process for it to output better. We need to build additional facilities to mitigate environmental problems. And now this increased complexity leads to more risk. And then finally, this risk just feeds back to now we need to make it safer. Now we need to make it better. Now we need to do more. And this is what I like to refer to as the loop of the feedback loop of irony. And this is why we do what we do. This is why we develop advanced process monitoring methods, because the current methods can't keep up with the rate of increase that we're seeing. All right? So before I move on to the energy graph-based visualization algorithm that I'm building on today, I would like to introduce the practical process that we considered as a case study here. So we considered a simple, continuously stirred heated tank reactor. So we can see we have a single tank. The tank is being stirred. We have a heat exchanger coil that runs through. And we have 2 control loops. One control loop to control the level in the tank, and a second control loop to control the temperature in the tank. And then this is our practically built benchmark. You can see the blue tank in the middle. The blue tank in the middle is what you see here. The big blue tank at the bottom is our cold water feed supply, and it returns to the tank as well. And then we have a geyser or a hot water reservoir for the heat exchange component that runs through the tank. Okay, so now I'll introduce the energy graph-based visualization fault detection algorithm. This is existing work. You can refer to our paper for more info. We have applied this method to many more complex processes, but for the purpose of this study, I'll just introduce what it entails. So if we take our P&ID diagram, the first thing we do is we identify the main process components. So the first process component would be our heat exchange component, and the second component will be our storage component, and then the last component will be the joint environment surrounding the process. And then we can build an energy graph from this. So we can see we get heat exchange into our tank and then out of the tank as well. We get cold flow into the tank and out of the tank as well. And this yellow line is our energy transfer. So if we look at the E variables, these are our rate of energy transfer. And then when we account for all of them, we can actually evaluate the B variable, which is our change in rate of exergy exchange. Okay? If we then take this graph, any graph can be represented as a matrix. So offline, we have ideal energy transfers all over our plant, which means we can take these ideal values and build a singular matrix, which is our NSREF matrix, or our node signature matrix. But then online, we will have for every process variable that comes in, we can calculate the energy associated with it. Okay? So then we will have for one process sample, for a second process sample, and for a third process sample. And then we'll have online multiple variants of the same matrix, but these are our online values. All right, so if we then take our singular or single NSREF matrix, and we consider all our separate matrices that we monitor online, we can conduct a comparison. And we can conduct our comparison using the HEOM method or the Euclidean heterogeneous overlap method, right? And this comparison, comparing the single matrix with these multiple matrices, results in what we call cost matrices. And that cost matrix is essentially just a difference between what we want and what we're monitoring at the moment. And we will have multiple of them as well. And then the final step would be to conduct eigenanalysis or eigendecomposition on our square matrices or our cost matrices. And then, of course, we will have multiple of these as well, each for every process sample that we take. And then we continue and monitor each element in our eigen results, which is the eigenvalues as well as the entries of the eigenvectors. And then we can get a fault detection graph over time for each eigenvalue and eigenvector entry, right? So that's normal, and then suddenly there's a fault at sample 900. But today I would like to focus on the middle part of the algorithm, which is the cost matrices and the eigenmatrices, all right? So now we move on to the specific problem statement, which is, if we take a look at our cost matrices, they are square, and then we should know that these, from the math shows and from previous studies, we know that these matrices tend to be asymmetric, which implies that if we look at our eigenvalues and our eigenvectors, the first thing we should know is the eigenvalues and the eigenvectors may not be in the real domain. Okay. This is not a problem per se. We do have methods to handle the imaginary component, should it come out. But it would certainly be nice to just stick to the real domain in this case. It makes computation much simpler, and we don't have to account for the imaginary domain. All right? And the second thing we should know is that eigenvalues, because this is asymmetric, the eigenvalues may repeat, which means these cost matrices may not be diagonalizable in the first place, which means we might end up in a situation where we get a singular matrix. And that is quite important because we want unique eigenvalues, and we want to maintain a full set of eigenvectors to monitor as part of our fault monitoring solution. All right? So how can we solve this? A specific research question now comes in. How may CK1, CK2, CK3, which is our cost matrices, be made symmetric? And this is what I refer to as spectral conditioning. How can we make them symmetric? And then subsequently, if we make them symmetric, do these spectral conditioned CK matrices produce improved fault detection results within this EGBV algorithm, this energy graph-based visualization algorithm? Okay? So we introduce the SSC and the HSSC approaches. I call them approaches, but typically they are just variants and modifications of the existing method, right? So this is our standard comparison method. This is the method that results in our cost matrix. And this is a typical example of what we will get as a result for a cost matrix, right? It's clearly asymmetric. And in the numerator, you can see we basically subtract the graph, the reference graph or the reference data from our sample data, and we normalize the data using our a range calculation based on the reference matrix or NSREF. Okay, but if we compare using what we call the sample self-comparison method, and the only difference here is instead of subtracting NSK from NSREF, we subtract NSK from NSK, but it's a sample by sample, comparison. So it looks like this would result in 0, but it's actually not. These are the differences between different nodes in the system. So we take node 1 and we subtract node 2. We take node 3, we subtract node 2. And then we will be actually able to get a symmetric result. But now, note that the diagonal in this case is actually full of zeros. And this looks to me like loss of process information, because this is valuable process information that we originally captured on the diagonal. Now we only have the off diagonals as a process informer. All right. So now we can also take a step further and introduce the HSSC method, which is a piecewise function. The diagonal is calculated the original way, like that. So we subtract, for the diagonal entries, we do this. But for the off-diagonal entries, in this case, we do this. Okay? And then we get a result that is symmetric and has populated entries on the diagonal. So now we move on to our results, for fault detection results. Just before I start giving you the results, I want to clarify that for this study, we focused on fault detection specifically. That's the first thing. The second thing is we only focused on the performance of the eigenvalues. not the eigenvectors as well, as we would typically do. And then the last thing is to evaluate the performance of our results, we use the receiver operator curve metric, which then flows into the area under curve evaluation, which is basically just a way of doing a threshold scan over our result, and then stating how well do the normal samples can be distinguished from the faulty results. So this is our eigenvalue 1 result over time, number 2 over time, and number 3 over time, and it's very clear that our HSSC method, which is the hybrid method, has a very exaggerated response. We can see that the blue, the SSC response is very muted, but don't be fooled, it has a very low noise profile. It is actually very possible to clearly still distinguish between the fault and the non-fault area, even though it doesn't look like it visually. If we go on to our area under curve evaluation, which is basically just a division being made from our false alarm rate versus our true alarm rate, we can see that if you evaluate the average of the 3 responses using our AOC result, in this case, the HSSC method has performed the best, and the standard result actually outperformed the SSC method in this case. Just for extra information, a value of 1.0 would be perfect. If it's a value of 1.0, it means the faulty samples are very clearly distinguishable or exactly distinguishable from our normal results, and a value of 0.5 would mean the fault samples are definitely not distinguishable. If we look at fault 2, which is a leakage in our system, we have eigenvalue 1 response, which shows a very clear response for the standard and the HSSC method, as well as the SSC method. In eigenvalue 2, our SSC method performed very well. And then in the last eigenvalue 3, all of them performed admirably as well. And then if we look at our results, in this case, the SSC method has outperformed all of them. The HSSC method came in second, and the standard method with a 0.83, which is not bad, but is not as good as the other methods. And then our last fault that we considered was a stuck valve fault. Eigenvalue 1 response shows very exaggerated results, not clearly distinguishable. Eigenvalue 2 showed very good results for the standard and the HSSC method. The SSC method also performed quite well, even though it doesn't make as big as a jump as the rest. And then finally we have eigenvalue 3, and then our results shows that the HSSC method has performed the best in this case. It's not as high as the other faults, or the previous tested faults. In second is the SSC method, and then the standard method is last here with 0.66 on average. Okay, so our conclusion and recommendations for this is we applied spectral conditioning. This is basically symmetrifying our cost matrices in this case within the standard EGBV method with focus on fault detection. 2 methods were proposed as modification, the sample self-comparison method and the hybrid sample self-comparison method. Both of these methods improved detection performance in a practical, continuously stirred heater tank reactor. And this is very important, without additional calculation. We basically took the original comparison method and modified it slightly, and were able to obtain better results here. Recommendations for this is we need to still test this SSC and HSSC methods on other, more complex processes for further validation. All right, this is very important because this is a very simple, albeit practical, which has its own difficulties, but a simple process nonetheless. We still need to conduct a study to formally compare these results with SVD, because SVD is also a very nice way of obtaining a symmetric matrix. If you apply SVD on a square matrix, the singular values and the singular vectors will also be perpendicular to each other. They will also be in the real domain, and this is a nice existing method that we can use as a benchmark to compare our study with. The third point, to verify any performance improvement regarding fault identification. As I mentioned, we focused on the fault detection results only. The strength of this algorithm that wasn't covered in this study actually lies in the fault isolation performance, which means pulling in the eigenvectors as well, and considering the eigenvectors as well as a fault signature. And we still need to evaluate this. And yeah, this is the conclusion of my study. Thank you very much for your attention.
We have time for some questions.
Thank you for the presentation. I would like just to ask, when you pose the question whether you can symmetrize your matrix, the first thing that popped out in my mind was to add its transpose and divide it by 2 or something like that.
Yes.
So is it a possibility or?
Yes, we actually looked at that. So it's interesting if you take a look at the difference between eigendecomposition, which is only applicable to square matrices, and you take a look at how singular value decomposition works, which is very closely related. The two are related to each other by the matrix multiplied by, or the transpose of the matrix multiplied by the matrix itself. So in this case, it would be C transpose multiplied by C. So it's interesting, you can either do eigendecomposition on C itself, and then you will obtain results. But as soon as you take C's transpose multiplied by C, get a new square matrix and do eigendecomposition on that would be equivalent to singular value decomposition. So what you're proposing, I understand as we can actually take, or what you're proposing is we do singular value decomposition. You just described the algorithm of singular value decomposition.
Well, actually, I had in mind to add those matrices, not multiply them.
Oh, okay. Well, that's a valid recommendation. I would like to chat afterwards about that. That'll be extremely helpful for the study.
Okay, thank you very much.
Thank you so much.
We have time for more questions. Anyone? Just a small question.
Sure.
Regarding the faults you provocate in the system.
Yeah.
How did you provocate these faults?
How did I create these faults?
Uh-huh.
Sure. So I believe one of the faults were a sensor fault. So remember that this is a practical system. We used a Siemens PLC to control the process. So for the sensor fault was conducted on the temperature sensor. And because this is a feedback loop, what we did was we added a segment on the PLC that at a certain time, we take the input measurement and we just add a constant value to the temperature before it goes into the controller. So now the system thinks it's controlling a deviated temperature. So that's what we did for the temperature fault. For the stuck valve fault, we basically, at a certain time point, disabled our controller, or we forced a fixed valve open value on our valve. So where it would normally control between 10% open and 30% open, we now forced it, I think, to be 22% open, some random value. That is our stuck valve fault. And I believe the leakage fault was the third one. So the leakage fault was conducted on the cold water inflow into the tank. And we actually mechanically, when we designed the process, we designed a bypass line that does not run into the main tank, but as the flow comes in, some of the flow gets diverted back to the reservoir, as if there would be a leakage, and some of the water doesn't make it into the tank, but gets lost in translation somewhere else. And so we would, at a certain timestamp, just open the side valve, and some of the water would be redirected, which then forces the control system to react and sort of try to stabilize at a new point. And that is sort of a step response that we also try to see in our faults. So those are the 3 faults that we investigated here. Some of them were implemented mechanically, and other were algorithmically emulated using the Siemens PLC.
Okay, thank you very much for the presentation. We're going to continue with Professor Adaptive Filtering Against Sensor and Actuator Faults. for Professor Hachishev.
Title of my presentation, Adaptive Filtering Against Sensor Actuator Faults. Outline, then mathematical models will be given, robust adaptive Kalman filtering, sensor actuator fault detection and isolation will be presented, fault-tolerant estimation of UAV dynamics, results, and conclusions. In aerospace control systems, sensor actuator failures can deteriorate the closed-loop performance considerably. Such failures must be diagnosed as quickly as possible and actively accommodated to arrest the performance degradation. Sensor actuator fault detection and isolation can be achieved by employing model-based fault detection and isolation techniques. And many model-based FTI techniques have been developed to detect faults by using Kalman filtering approach. Kalman filtering approach to state estimation is quite sensitive to any measurement malfunctions. If the real-time condition of system doesn't correspond to the model used in the synthesis of the filter, then the adaptive Kalman filter can be used to recover the possible malfunctions. Adaptive Kalman filter is used to tune the measurement and process noise covariance matrix, the measurement noise covariance matrix and process noise covariance matrix, respectively. When the process noise covariance matrix is scaled, it is named Q adaptation. That means there is an actuator fault to be compensated. Otherwise, when the measurement noise covariance matrix is scaled, it's named R adaptation. In this case, measurement fault to be compensated. In this study, the combined fault isolation and R and Q adaptation procedures are solved via one robust adaptive Kalman filter incorporating the R and Q adaptive filters. After detection of fault, it is proposed to run simultaneously R adaptive and Q adaptive Kalman filters to distinguish sensor and actuator faults. For the fault isolation purpose, estimation performance of the R adaptation and Q adaptation procedures are compared. As the estimation performance criterion index, it is proposed to select sum of quadratic differences between estimation and extrapolation values of investigated filters. The proposed method in this study is applied to unmanned aerial vehicle dynamics. The UAV motion includes the longitudinal and lateral motion dynamics. The longitudinal equations of motion equation is the state vector of longitudinal motion, forward velocity, vertical velocity, pitch rate, pitch angle, and altitude. System matrix, control distribution matrix. As control inputs, the deflections of elevator and thruster are used. And lateral motion. As lateral states, the side slip angle, roll rate, yaw rate, and roll angles are used. System matrix, control distribution, and as control inputs, deflections of ailerons and rudders are used. We combine longitudinal and lateral equations into one equation and compose the extended state vector, which includes the longitudinal and lateral states. And the mathematical model is linear. Therefore, the linear Kalman filter for such combined linear dynamic system can be used. The Kalman filter equations, state prediction, covariance, innovation. Innovation is the important concept in Kalman filtering. If the system operates normally, the normalized innovation is the white Gaussian noise with zero mean and unit covariance matrix. And thanks to this property, innovation is widely used in fault detection and isolation problems. And the rest of equations of Kalman filter, innovation covariance, optimal Kalman gain, state estimation, and covariance estimation. Our adaptation filter. The innovation sample covariance matrix is proposed to be used for the sensor FTI purpose. Expression for the sample covariance matrix can be written in this form. M is the width of sliding window, the innovation vector. It's proposed to use matrix built of multiple measurement noise scale factors to fix the relevant terms of measurement noise covariance matrix and consequently the Kalman gain. In order to determine the scale matrix, the real and theoretical values of innovation covariance must be compared. Real innovation covariance and theoretical innovation covariance. In the case of any measurement malfunctions, real innovation covariance will exceed the theoretical innovation covariance. Hence, if a multiple measurement noise scale matrix is added into the algorithm and from this equation, the scaling matrix can be determined in this form. And sensor fault accommodation algorithm can be written in this form, the Kalman gain and scaling matrix. In the case of any measurement malfunctions, the scale matrix will increase. That brings out the smaller Kalman gain, which introduces the influence of innovation on the estimation procedure. As a result, the more accurate state estimates can be obtained. Co-adaptation. In case of actuator fault, the real innovation covariance will exceed the theoretical one. Thus, the basis of multiple system noise scale matrix determination is obtained and appropriate multiple matrix such that the real and theoretical values of innovation covariance match. Hence, the system noise scaling matrix built of multiple scale factors is added to the algorithm in this form. Here, the real covariance and theoretical covariance. And from this equation, the scaling matrix can be found in this form. And actuator fault accommodation algorithm is obtained in this form. And the sensor actuator fault detection algorithm. Normalized quadratic innovation is used as monitoring statistic. Here, innovation vector, innovation covariance, theoretical covariance. The quadratic form has the chi-square distribution with n degrees of freedom, n is the dimension of the innovation vector. By selecting the level of significance alpha, the threshold value for chi-square distribution can be found. And if the normal monitoring statistic exceeds the threshold value, the fault is detected. And sensor actuator fault isolation. As the estimation performance criteria index, it is proposed to select quadratic differences between estimation and extrapolation values of investigated filters in this form. It is the squared residual, estimation, and extrapolation values. As estimation performance criteria, it is proposed to select some of M realizations of epsilon after detection of fault in this form. And the general block scheme of the proposed method, initial values, then prediction of Kalman is calculated, prediction covariance, and innovation, the difference between the measurements and extrapolation values. The monitoring statistic is calculated and the threshold value is determined. If the monitoring statistic value less than threshold value, it means that no fault in the system and the procedure continues with the conventional Kalman filter. In the case of monitoring statistic exceeds the threshold value, in this case, it is proposed to run simultaneously R-adaptive and Q-adaptive filters and calculate their performance criteria. If the performance criteria R-adaptive filter less than Q-adaptive, this indicates a measurement fault and procedure continues with R-adaptive filter. Otherwise, if performance criteria Q-adaptive is lesser than R-adaptive, this points actuator fault and procedure continues with Q-adaptive filter. And experimental study, the small UAV is chosen and Kalman filter applications are performed by regarding the dynamics and characteristics of that UAV. During simulations for testing FT algorithm, two kinds of measurement malfunction scenarios are taken into consideration. Continuous bias is additive measurement fault, and noise increment fault is the multiplicative measurement fault. And results. The behavior of statistic, it is squared residual. In the presence of pitch angle gyro bias, when R-adaptive and Q-adaptive filters are used, the results of R-adaptive filter. As seen, squared residual doesn't change significantly. And here, Q-adaptive filter change rapidly. And the performance criteria, sum of 20 realizations, where fault occurs, and sum of 20 realizations of epsilon for R-adaptive filter and for Q-adaptive filter. As seen, performance criteria R-adaptive filter is significantly smaller than Q-adaptive filter. This indicates measurement fault and procedure continues with R-adaptive filter. And here you can see the estimation results, R-adaptive filter results and Q-adaptive. Fault occurs, bias fault occurs at the iteration 30 from till 60. And the R-adaptive filter gives sufficiently good estimation results, and Q-adaptive filter fails and gives the biased results and filter diverge in this interval. The procedure continues with R-adaptive filter. Second scenario, noise increment type measurement faults. Behavior of statistics, you can see in figures. R-adaptive filter results and Q-adaptive filter. R-adaptive filter change insignificantly, 0.6 here, and here 50, 60. Changes rapidly. And the performance criteria values for R-adaptive filter and Q-adaptive filter. As seen, R-adaptive filter performance criteria values is significantly smaller. This indicates the measurement fault and procedure continues with the R-adaptive filter. And you can see estimation results. Here you can see the small deterioration in R-adaptive filter, 0.5 here, but here 5. And Q-adaptive filter fails and gives inaccurate results. And the third scenario, actuator fault. Actuator fault is simulated by multiplying the first column of control distribution matrix with a small number, in this case 0.1, which fault corresponds to loss of effectiveness, loss of control effectiveness of elevator. And the actuator fault occurs. As seen in this case, Q-adaptive filter performance criteria is smaller, and sum of 20 realizations, R-adaptive filter and Q-adaptive. In this case, Q-adaptive filter performance criteria is significantly smaller than R-adaptive. It points to actuator fault and procedure continues with Q-adaptive filter. And you can see estimation results here. R-adaptive filter fails and gives biased results, but Q-adaptive filter gives sufficiently good estimation results. And conclusions, novel adaptation procedure is proposed with an approach of making choose the R-adaptation or Q-adaptation strategies. In the novel method, after the detection of fault, it's proposed to run simultaneously R-adaptive and Q-adaptive Kalman filters and compare their estimation performances to distinguish sensor and actuator faults. As the estimation performance criteria index, some of quadratic differences between estimation and extrapolation values is used. The proposed approach doesn't require the additional photoresistant filter. It is the main advantage of the proposed method. Thank you for your attention.
We have time for questions. Any question? No question? Okay. Thank you for your presentation. Just a small question. You said that adaptive filter is better than the Kalman filter, but how do you tune the Q and R matrices of the Kalman filter without adaptation?
How adaptation?
Without adaptation, you have to tune Q and R matrices from the Kalman filter. No? There is a chance that are not tuned properly?
Yeah, two ways to adapt the Kalman filter. One, to estimate the measurement noise covariance or system noise covariance, and the second method, scaling of this matrix. We choose the scaling method. We scale this matrix. In the case of animal functions, the noise matrices change, and we determine how change scaling from equality of real and theoretical covariance matrices. Real and covariance matrices should be matched. And from this condition, we determine the scaling matrix, and scaling matrix ensures the adaptation of the Kalman filter.
Okay, thank you very much. The last presentation for Professor Hajiyev, fault detection statistics in the presence of additive measurements.
The title of presentation, fault detection statistics in the presence of additive measurement errors. Outline, introduction, then problem statement will be given. Kalman filter innovation for fault detection will be explained. Sensor biases and actuator faults impacts on innovation will be investigated. Then fault detection statistics based on trace of non-central V-shaped matrix will be presented, and the results and conclusion. It's possible to detect faults in dynamic system using Kalman filter innovation. The innovation, if the system operates normally, innovation is a white Gaussian noise with zero mean. And monitoring can reveal deficiencies that change the statistical properties of innovations. Innovations-based FTI methods have the following benefits. In contrast to most algorithmic methods, they require little computational expenditure for realization, enable real-time fault detection, problem solving, and don't require a priori knowledge about change of statistical characteristics to innovation in the case of fault. Real condition of operational of dynamical system, solution of the problem of estimating and state parameters of system in most cases has to be carried out in the presence of systematic measurement errors, the average value of which is not equal to zero. This case takes place in inertial navigation systems due to the characteristics of the elements of INS, accelerometers, and gyroscopes, accuracy characteristics of position and velocity deteriorate over time. INS errors grow slowly over time and can reach large values. INS errors have both systematic and random components. In most cases, in practice, it's assumed that INS operates in a linear mode, and the measurement errors are additive. Problem statement: despite a sufficient number of publications about innovation test, the influence of bias type sensor actuator faults on the innovation of Kalman filter has not been investigated properly. It is necessary to develop fault detection statistics that are not significantly affected by additive INS errors. In this study, influence of sensor biases and loss of control effectiveness type actuator faults on the innovation process are investigated, and the innovation approach based new sensor actuator fault detection method using trace of non-central V-shaped matrix, which is sensitive to change the innovation mean of Kalman filter, is proposed. In this study, the Kalman filter is used. The mathematical model of unmanned aerial vehicle is used, and Kalman filter is applied to this model. And Kalman filter equations, you can see: state prediction, covariance, innovation, covariance, optimal Kalman, state estimation, and covariance estimation. It is important to investigate impact of sensor actuator faults of the innovation. The sum of theorems is proved in this work. Theorem 1, if Kalman filter processes the measurements and the measurement bias fault occurs at iteration tau, then at all iterations more than tau, innovation bias is equal to the difference between the measurement bias and predict observation bias. And the theorem 2, if Kalman filter processes the measurements and actuator bias fault arises in the ICE actuator at iteration tau, then at all iterations more than tau, the innovation bias is equal to the product of the difference between the actuator bias and prediction bias with measurement matrix. These theorems, results of this theorem, show that the sensor and actuator bias type faults affect the innovation, the sequence of Kalman filter, and change the statistical characteristics of innovation. The traditional method for fault detection is the cumulative fault detection statistic. This is the traditional method, is known method. Cumulative fault detection statistic is written in this form: the innovation vector, innovation covariance, and width of sliding window. This statistic has chi-square distribution with ms degree of freedom. S is the dimension of innovation vector. By selecting level of significance alpha, threshold value can be determined, and if the monitoring statistics exceeds the threshold value, fault is detected. But this statistic doesn't take into account the systematic INS errors. And the proposed statistic: in the presence of systematic measurement errors, the innovation sequence will be white Gaussian noise with zero mean and covariance. As can be seen, innovation has zero mean, is not zero, average of innovation. The innovation sample covariance is proposed to be used for the sensor actuator fault detection. The matrix, this matrix has non-central V-sharp distribution with n degrees of freedom and non-centrality parameter. As seen, the non-centrality parameter includes the non-zero average of innovation vector. Innovation bias will cause a change in mathematical expectation of the trace of random V-shaped matrix. Therefore, the trace of V-shaped matrix can be chosen as the monitoring statistic in the fault detection problem. Trace of the non-central V-shaped matrix has non-central chi-square distribution with m-1 s degrees of freedom and non-centrality parameter. Non-centrality parameter. And checking the trace of non-central V-shaped matrix. The proposed approach to test the trace of the non-central Wishart matrix is based on the use of first cumulant of this matrix. The R's cumulant of the random matrix can be written in this form. As known, the first cumulant corresponds to expected values. The second cumulant corresponds to variance. Substituting instead of R1, we obtain the formula for expected value, and substituting instead of R2, we obtain formula for variance. It is shown that when n approaches to infinite, the expected value of this parameter, trace of non-central Wishart matrix dividing square root n, approaches to the product of trace of theoretical innovation covariance with square root n. And variance of this value approach to this value. For large value of n, chi-square distribution approaches to normal distribution. In practice, the chi-square distribution is considered normal when n more than 30. And when n more than 30, the distribution can be considered as normal distribution. If trace A is normal distribution, then this normal distribution value minus the expected value dividing the standard deviation gives standard normal distribution with parameters 0 mean and unit variance. And we convert the non-central Wishart matrix to standard normal distribution using this transformation. By selecting level of significance alpha, the threshold or quantile of standard normal distribution can be determined from this equation, and upper and lower bounds are determined for standard normal distribution. And decision rule for sensor actuator fault detection in this case can be written in this form. If the trace of non-central Wishart matrix lay between lower and upper boundaries, no fault occurs. If trace exceeds one of boundaries, fault is detected. And this method is applied to unmanned aerial vehicle dynamics. The longitudinal and lateral equations are taken into consideration. You can see the longitudinal motion of UAV. The longitudinal state is forward velocity, vertical velocity, pitch rate, pitch angle, and altitude. And lateral dynamics, side slip angle, roll rate, yaw rate, and roll angles. We combine this dynamics into one equation and compose the state vector, which includes the longitudinal and lateral status, and apply the Kalman filter to this model. And results, scenario 1, constant bias faults in measurements. Behavioral statistics, the proposed statistics based on non-central Wishart matrix trace, and the traditional statistic. In the presence of gyro drift and constant sensor bias. The constant sensor bias is added to gyro measurements between this interval, 40 and 60. And gyro drift is introduced to gyro measurements from beginning Kalman filter. As seen, both algorithms detect the fault, constant bias sensor fault, and gyro drift strongly affects the values of the traditional statistics, but doesn't affect significantly to the proposed statistic. Scenario 2, and estimation results in the presence of gyro drift and constant sensor bias. You can see the constant sensor bias interval, the filter fails and gives biased results. And you can see a small deterioration here, small bias due to the gyro drift, but it is not fault. It can be corrected using adaptive Kalman filter. And scenario 2, loss of control effectiveness type actuator fault. Actuator fault is simulated by multiplying the first column of control distribution matrix with small number. This fault corresponds to the loss of effectiveness of elevator. Actuator fault is introduced in this interval between 40 and 60. Both algorithms detect the actuator fault, but gyro drift strongly affect the values of traditional statistic, but the proposed fault detection statistic is not significantly affected by the INS drift error. And the estimation results in this interval, actuator fault, interval where actuator fault, the filter gives inaccurate results, biased results, and there's a small bias due to gyro drifts. And conclusion, an innovation-based central actuator fault detection method based on the trace of non-central Wishart matrix that's sensitive to changes in Kalman filters innovation is proposed. As a difference from the most of existing innovation-based fault detection methods, the approach allows to detect faults in the presence of additive measurement errors. And simulation results show that gyroscope drift errors strongly affect the values of traditional monitoring statistics, but don't significantly affect the proposed fault detection statistic based on non-central Wishart matrix. Thank you for your attention.
Thank you. We have time for some questions. Anyone has a question? Just a small question. You said you are using an UHV, no? Which UHV?
UAV? It's a small UAV, about 2 kilograms.
It's a plane, it's a quadcopter, I don't know.
For experimental.
Yes, because you didn't say that.
For our experiments, a small UAV, mathematical model, we have UAV, and we apply our algorithms to test our algorithms on this UAV.
Yes, because I saw the mathematical model and it was linear.
Linear, yeah.
Yes,
linear
yes.
right model.
Linear
right model.
Yes, but I didn't saw any masses, or I don't know which parameters you are using there, no? Because you didn't show the experimental.
Yeah, that's simply a model.
Okay. Thank you very much for your presentation.
Thank you.
And with this, we are finishing this session. Thank you.
My name is Ivo Punčochář, and I will be chairing this session. Co-chair isn't still here, but it doesn't. I hope it doesn't should delay us to start the session. So the session is entitled Health Monitoring and Fault Diagnosis Applications, and the first paper will be presented by Andrea Mattoni, and the title of the paper is Step Towards Implementation of a State Observer in Industrial Aluminum Smelters. So, thank you.
Okay, do we have a pointer? So, hello to everyone. Thank you for participating to this session. In this presentation, I will talk about the paper entitled The Step Towards Implementation of State Observers in Industrial Aluminum Smelter. And this project has been in collaboration with the Rio Tinto company, that is a multinational company that between the other activities, they are producing aluminum. In this presentation, I will first introduce the process of aluminum smeltering for the people that doesn't know that. And in the right side of the slide, we have an actual aluminum smelter where you can see in the left side of the picture some steams of the anodes that are synced inside a cryolite bath. And the bath is inside the machine at the level of the floor. And so somehow just to give you some context. And here you can see that there are 12 anodes, and on the other side of the machine you have other 12 anodes. So it's a quite big machine of around 20 meters to 3 meters. Then we will do some modeling of the process and develop some observability concept and doing some observability design. And at the end we will try our observer in a simulator and also on real data coming from the smelter. So in this presentation and in this work, we doesn't consider the distribution of the alumina dissolved in the bath, but we are considering as the smelter is only composed by a single anode, as you can see in the picture, and in the bottom of the picture you have the cryolite, what I was telling about you before. That is liquid, in the liquid side, and it is heated at around 900 to 1000 degrees. And you have alumina, that is what we need for creating aluminum, and the electrolysis process is, the objective is to separate aluminum from the oxygen. Here we put the alumina inside the cryolite that melts, and when the alumina is melted, we apply a current to the smelter, such to initiate the electrolysis process. And the electrolysis process creates from one side the aluminium, then deposits inside the smelter, and on the other side creates carbon dioxide that goes in the atmosphere. So what are the more important variables in our process that will allow us to look at the states of the machine and somehow do some diagnosis about it. And first of all is the dissolved alumina that is defined as the quotient between the bath mass and the alumina mass. Then we have the anode to cathode distance, where the anode is the one that we have in the figures, and the cathode is the actual aluminum that is created during the electrolysis process. And the third one is the pseudo-resistance that are actually the signal that we have available and that we will use to estimate the other quantities. And the pseudo-resistance is defined as the voltage that we have, that we can measure, minus a certain constant that I call K0 that depends on the machine that we are using. Depending on the machine, the K0 can vary. And the I line is the current that we are using for creating the electrolysis. First of all, we have to look at the relation between the pseudo-resistance and the quantity that we want to estimate in our process. Here is there's figures that represent this relation, and here we can see that the resistance goes up as soon as the dissolved aluminas diminish, until to a certain point where we have what we call an anode effect, that is the fault that we have in our machine, and we want that the machine goes and arrives to this situation where an operator intervention is needed. And so we don't want to do that. And overmore, there are some, the chemical reaction that takes place changes, and we have the creation of the CF4 gas that is very polluting, and so we don't want this for the environment either. Another important quantity is the feeding frequency, how it is feeded the machine. Actually, we have the feeder that we had also in the previous figures that is not actively and constantly pouring the alumina inside the bath, but every period seconds of time, it's activated and 1 kilogram of alumina is dropped inside the bath. And so what we can actually control is this period. And the input to our system is not the period itself, but is the frequency, so 1 over period. Okay, having this in mind, now we'll talk how they are nowadays controlling this kind of machines. So one can say, okay, very good, if we know how much the aluminum smelter is consuming, I will put a quantity of aluminum that will allow the dissolved alumina to stay constant. But actually this is not possible because they don't know this, the consumption quantity of alumina, and therefore, since this depends a lot on the environment on which it is the smelters, can vary also during the day. So this is not known, and what they do is here we have FT, that is the theoretical frequency, that is the one that makes the alumina theoretically constant, and they on purpose put it slower. And so what it happens is that the alumina decrease, and the alumina decrease reflects on the signal that you have available, an increase in the resistance, as you can see in the third graphs. Then, once the derivative of time on the resistance arrive to a certain value, they switch the control, and they on purpose put it more than it's needed, and the resistance goes down, and the resistance with respect to time again goes down, and this cycle is repeated over and over again. Okay, so now that we have the background, we try to go down in the modeling of the process and try to also explain why they are doing that, why they are controlling like this, and if it has some sense or not, this way of controlling the machine. So as a model, we propose the one that I put in the picture. The feeding frequency passes first to an input filter and then to a second block that simulates the alumina dissolution. And only after this, these two quantities, so the flux of dissolved alumina, goes inside a mass balance model. And the mass balance model is the one that you have in the equation down. And here, just not to be worried, in the first equation is the balance of alumina, so the one that is consumed by the electrolysis, and the one that is injected in the system by dissolution. The ACD is the distance between the anode and the cathode. And here in the first term, we have together the fact that the anodes consumes and the aluminum is created. And it's negative because the aluminum is created more fast than the consumption of the anodes. And so ACD normally goes down. And BM is the fact that we can control all the anodes in the smelter to move all together. And finally, this is the first contribution of our paper, where we propose a certain expression for the pseudo-resistance that depends on the dissolved alumina and ACD. And this expression is already known in the literature, but it has a very complicated form, physical form. And here what we wanted to do is to simplify this physical expression to have something that we can use for analysis. The second contribution of this work is the adding of a third state variable that we call the aluminum sludge. And this somehow physically the alumina non-dissolved that accumulates between the interface between the aluminum and the cryolite. And this is somehow what physically explains what we have observed in industrial data, the so-called hysteresis of the resistance. This is very often happen inside the industrial application, so we somehow figured a way to easily model and integrate it in the model. Once we have the model, what we want to do is to design an observer. But first, before designing an observer, we want to know if an observer can be designed and in which condition the observer works. So we came up with this proposition that has been proved in the paper, and that I can read. The mass balance model is locally weak observable in its state space, and it admits a singular input for which observability is lost, given by U2 equal to alpha 1 E-line. What does this mean? In this way, you have to know observability theory to know about it. So I try to translate in an applicative way, such that has some meaning in application. First of all, what we have to observe is that our system, the model that I presented before, is nonlinear. And so nonlinear system has to, we have to use some nonlinear observability tool to understand if the system is observable. So first of all, okay, we assume that the industrial process that is perfectly modeled by our system, that of course is not the case, but to do some analysis and some speculation about this proposition, we have to assume that. Then, what we have to do is that the input that we have in our system should stay away sufficiently far from this value. Because in nonlinear system, the observability depends on the input that we apply to our system. And this input, if we look a little bit closer, exactly correspond to the input that maintain the alumina constant in our system. And if we remember at the beginning of the presentation when I explained how it's actually controlled right now the smelter, actually they are doing exactly like this. They never put the alumina feeding inside our smelter such that it maintains the equilibrium, because they had to somehow estimate something. And actually we demonstrated, we proved it, that this is actually the input that we cannot put inside our system if we want to observe it. And finally, if this is done, an observer that converges to the real state when its initial condition are sufficiently close can be designed. So what we do next is designing this observer. And to do that, we have proposed first a change of variable, because with this change of variable, we are in some coordinates that help the observation, and it makes the observer design a little bit more simple. So we came up with a system in this state space form, and we apply a classical extended Kalman filter that everyone knows. I will not go into details because it's really the classical one that we can find in the literature. So after this, we apply it to a simulator. So before applying it to the real system, we want to make sure that at least at the simulator, the things are going well. And here what we can see is in the first part of the picture, we have the feeding frequency that we took it from a real smelter. It's not exactly as they showed before, but as this overfeeding and underfeeding concept. Here we have the resistance coming in red from the simulator, and in blue, the filtered version by the observer. And here we can see the three states variables that we are estimating that start from three different initial conditions, and we see that after some time they converge to the same estimation. So this gives us, okay, theoretically and with the simulation, we know that our observer is working. Then we apply it to a real case. Here we have 20 hours, around 20 hours of working of a real smelter. The first is always, the first picture is always the feeding frequency, and then the resistance in red. And afterwards, we have the estimation of the three states, where also we can observe in this figure that starting from different initial conditions, they all converges to the same estimation. This is really important because at the beginning of the estimation, we don't know the initial condition, and we want our estimation to not depend on the initial condition that we are giving to our observer. Okay, so some conclusions. First of all, we proposed a simple yet precise pseudo-resistance expression that allows us to do analysis. Then we proposed a model that takes into account the pseudo-resistance hysteresis. And we proposed also an observability study of the proposed model. And also the observer that we designed has been applied on simulation and on the data. Then the perspective. Of course, here I did not do a fault investigation, but one of the main objective of this project is to see when an anode effect is happening and somehow anticipate it as soon as possible. And to do so, first of all, we have to design a distributed observer that use the anode current that are passing through each anode to somehow have the estimation of the distributed dissolved alumina. Then what we want to do and what we are doing right now is use the anode current to do this distributed observer and do this, use this data coming from the observation for the anticipation of the fault and therefore of the anode effects. Thanks for your attention.
So thank you for the presentation, and now it's some time for questions, so please.
Do you have some experience about the robustness? Because I assume that in the practical world, really is not the model has uncertainties in all the parameters, and if you have made some analysis to test that it's going to work this in the practical case?
Yeah, thank you very much for the question. The main problem in this application is that we don't have measurement of dissolved alumina. So we cannot test if our observation is working or not. So a possible test to understand if our work is working or not is actually understand if it's good at anticipating these anode effects. This is the only way that we can test our algorithm, and is something that we plan to do in the future. So in this work, there is just a proof of concept and just a way that takes into account the different things and analysis to do something, and the observation that we made makes sense with reality. But the very proof of the this unfortunately, since the measurement, the available measurement are at an error of plus minus 1%, where the alumina is varying of around 0.5% during an over and underfeeding. So the precision of the measurement is very, very poor, and it's nowadays impossible to use it for confirmation, to understand the errors that we are doing. And so the only thing that we have is that makes sense with reality, and a possible way of doing stuff is take a look at the anode effects.
Thank you for your nice presentation. I was asking myself if when you develop the model, if the pseudo-resistance if you go to conclusions, if you decided to do the pseudo-resistance hysteresis after or together with the model, the first model itself?
Thank for the question. Yeah, actually, the first model that we tried was without the hysteresis, but we realized that the observer was diverging at some point using the real data, and so we start dipping inside the data that we have available, and so somehow was a process where we tried something, we understood that was not the good model, and then we start again from the beginning. And we tried different ways of hysteresis, one more complicated and other less complicated. And at the end, using this very easy way of applying this hysteresis, because looking at the model is not really an hysteresis, but models in the good way the data, we realized that we are doing a good job. So yeah.
Okay, thank you.
So let's thank the speaker again. And the next presentation will be given by Linda Bokella, and she will be talking about a two-stage machine learning-aided approach for quench identification at European XFEL.
Hello, everyone. Linda Bukela from DESI, the German Electron Synchrotron, and today I'm going to be presenting our work that we're conducting at the European XFL that deals with the quench identification with the help of a machine learning assisted approach. Sorry. Sorry. So as we all know, light has always been used to probe matter, and for those of you who might not be familiar with the particle accelerators, I think it's worth mentioning that these facilities can also be used in order to generate light, and that's the case with the European X-ray free electron laser, or simply the European XFL, which is considered as the largest particle accelerator for X-ray laser generation worldwide, as it is able to achieve an acceleration of electrons to high energies of up to 17 GeV and generate around 27,000 of extremely intense laser flashes per second. It is located in northern Germany, in Hamburg, as we can see it here. It spans over 3.4 kilometers. It starts its course at DESI and it ends at Schönefeld, where we have the experimental halls. Several hundred users benefit from the facility every year, therefore its availability is of tremendous importance. A brief overview on how the light is generated. First, the electrons are produced in the form of bunches and then propelled with the injector, also called the gun. These bunches are then accelerated through the LINAC, thanks to the superconducting technology of the superconducting radio frequency cavities. Later, the electrons are transformed into photons with the indulators, and finally, the laser light is produced and sent to the experimental halls. In our case, the most important part of the facility is the LINAC, where we have in total 25 stations, and where in each station we have 32 superconducting radio frequency cavities. So in total, in the LINAC we have around 800 cavities. In order to achieve this acceleration, the cavities that are considered or that act as resonators are driven with an oscillator at their resonance frequency, which is in this case 1.3 gigahertz. This creates alternating electric fields that does the acceleration of the charged particles, in this case the electrons. What we're looking, and these cavities within the stations are monitored and controlled with the LLRF system, or the low-level radio frequency system that aims to achieve a stable and a desirable accelerating field, which is around 23.6 megavolt per meter as an average. And the plots that we're looking at here represent the amplitude and the phase of a nominal RF wave, we have the forward wave, which is the driving wave, and since part of it is reflected at the coupler, we have also the reflected wave. And if we sum up these two, we get the standing wave inside the cavities that is called the probe. And the acceleration is achieved at this exact flat top of the probe by synchronizing it with the arrival of the electron bunches. And as we can see, these cavities are operated in a pulse mode with a repetition rate of 10 Hertz and a duration of 1.8 milliseconds per pulse. Obviously, the safe and optimal operation of this subsystem is crucial, and that's why we need fault detection and isolation. And in our case, we deal with the quenches that are considered as severe anomalies, and therefore priority for the LLRF experts. The quenches happen when the cavities, for some reason, heat up and lose their superconductivity, and therefore cause an operational downtime. The current solution that is implemented as part of the LLRF system is called simply the QDS, the quench detection system, and relies on the quality factor of the cavities. The quality factor, or simply the QL, is an indicator of power dissipation that is induced mainly by the coupling process. This QL turns out to be effective, an effective indicator of quench occurrence as well. And that's why, in order to do the detection, we rely on a running average that we get from the last 100 pulses. And then when computing the QL for each single pulse, if we detect a drop in the QL by typically 10% of the nominal QL, then an alarm is triggered through the QDS for a quench. The problem with the solution is the fact that it has robustness issues, as different events can lead to the drop of this QL, leading to an important number of false alarms. That's why another solution has been initiated, and because we have more RF data that could be measured and collected, the solution is model-based. It relies on the electromagnetic dynamics of the cavities. As we can see it here, we see that the equation represents the change of the standing wave that is influenced by the detuning and the half bandwidth. The detuning is basically the difference between the resonance frequency and the driving frequency, while the half bandwidth represents how sensitive the cavities are towards this detuning. And we also have another component here, which is the field that is induced by the beam. And this model here is given in the IQ domain. This model is exploited thanks to the parity space, with the parity space method, in order to get residuals. The parity space method is an analytical redundancy method that aims to obtain redundant expressions from the state space model that are based on the known variables, and that help then to get the residual. Later, a threshold is applied on the generalized likelihood ratio, which is a statistical test that is applied on the residual in order to detect any change in the mean of the residual. So here, we're having the K here, which is the size of the evaluation window. We have the evaluated residual, and sigma, which is the variance of the nominal residual. The advantage with this GLR is the fact that it can give us distinctive signature for the different faulty behaviors that have been seen within the cavities. For instance, we have this distinctive patterns for the quench with the GLR here. Here we are having the residual, and we have other faulty behaviors that are not identified yet, although for this one we already know that it was induced by the beam. Now, in order to isolate these quenches from the rest of the faulty events, we rely on a machine learning method, and that is the main contribution of this work. We use the K-Midoids algorithm in order to build a profile of these quenches. We use two similarity measures, namely the Euclidean and the dynamic time warping. The traces are normalized and or reduced, so they are reduced for the EUC as it is unable to capture the similarity of two traces that have some shift in time, while that's the advantage of the dynamic time warping. As we can see from this example with the DTW, the two we capture well the similarity of the two traces as compared to the EUC. With both models, we obtain two clusters and therefore two midoids. Here we're having results obtained with data from 2021, where we have 76 quenching GLR traces. With the plot, oops, sorry. With the plots here, we can see the frame of interest that we got by reducing these traces. And what we have noticed is the fact that this assignment has been achieved with respect to time of occurrence. So basically here we have the quenches happening at the end of the pulse, while here we're having quenches happening at the beginning of the pulse. In order to do the inference now, we look at the distance space, basically the distance of the quenches from the midoids and the distance of some validation data set from the same midoids. We then use thresholds and decision boundaries that are obtained from the quenching distances. The decision boundaries are obtained by having a fit to the distance, to the quenching distances, and it depends on the similarity measure. Here we're having, for the EUC, an ellipse that we obtain, as we've said, from these distances, and then we define a set of quenches. So basically, this summarizes this green area here, and this holds for the DTW, and in this case, we're having a polynomial fit basically the decision boundary is obtained by scaling the intercept of this fit. Now, when it comes to the deployment, it is offline for now. If we look at the stations again, we have different protection systems that are associated with the different subsystems of the stations, like the klystrons and modulators, etc. We call them the interlocks, and they are either firmware-based or software-based. And here we have the QDS, the quench detection system, as well. That is part of the LLRF system. Whenever one of these interlocks is triggered, data is saved to HDF5 files in order to be used in a post-mortem analysis. We have our residual generation method and the evaluation method with the GLR that are implemented as part of the trip event logger that has been developed by our colleague Jan Tim. That is running on a daily basis in order to get these residuals and the GLR and to be saved into the HDF5 files. These results are then exploited with the machine learning method in order to isolate and identify the quenches. Here, what is worth mentioning is that this trip event logger provides a user interface or graphic interface, a GUI, that helps that comes really handy when it comes to the labeling of the data that we know it is very hard to accomplish. And something that I would like to share as well is the fact that although the The solution is not online yet, but it can help to gain some insights as we are generating daily reports that can summarize the different events that, Yeah, so the different events that have happened in the last 24 hours. So we can see, like, for instance, the different stations that have tripped, the cavities, and the gradient here, and we also have some plots of the RF signals and the residual and the GLR, etc. Now, when it comes to the evaluation, we use data from 2022, where we've had 354 events. When we talk about events, we're talking about station events that were found to be faulty using the GLR, and 87 were found manually to be quenches. And we've used the true positive rate, the false positive rate, and the area under the rock curves in order to evaluate the different approaches. And what we have noticed is that we have improved the results mainly by reducing the number of false alarms, as we can see here, going from 54 with the QDS to 11 and 20 with the GTW and the EUC respectively. Now, in the future, we obviously still have a lot to do. We're having challenging patterns, for instance, as we can see them here, that need to be tackled. We need to go online. Therefore, the firmware implementation has already started. And we would like to explore more machine learning methods that we've initiated as well, and we are having promising results with the application of a convolutional neural network on the GLR. We also would like to have validate the results before going for an online fashion, and therefore we need more data. And in order to label these data, we need a smarter labeling strategy, and therefore maybe going for an active learning approach where we can have an expert in the loop strategy. So that was it for me. Thank you very much.
So thank you for a very nice, interesting application. Are there any questions? Okay, I might have one, just simple one. You were talking about generalized likelihood ratio test.
Yes.
And it usually means that you need to estimate some parameters in maximum likelihood sense. So what is the estimated parameter?
In our case, what was missing is the mean, because we do get the variance from. Sorry. Yeah, so here we do have the variance that we do get from the nominal residual. However, for the mean, we don't have an estimate for it. So we're using the MLE to estimate it, because we have this assumption that the residual is following a Gaussian process with zero mean for the nominal operation, while deviating from or different from zero when we're having a faulty event. Yeah.
Okay, thank you very much.
Thank you.
Okay, next presentation is given by David. Okay, and he will be talking about leak detection for household pipelines based on a smart valve with single pressure and flow sensors.
Good afternoon, everyone. So in this presentation, I want to expose you a leak detection for household pipelines on a smart valve with a single pressure and single flow sensor. So I start with a brief introduction for a leak detection problem. Then I show you the proposed smart valve, the application on a real case, the results, and the end, the conclusion. So let's start with the leak detection problem. Leaks in pipelines are a well-known problem that causes a waste of resources. And for our SIGNET context, manufacturer starts to build smart valves to detect flow in a household plumbing system. So the typical structure of a smart valve consists of an electrical electrical valve, an array of sensors, and an embedded control unit that install on the leak detection system that consists of a set of algorithms that analyzing the raw sensor data provide the leak and the leak detection decision. So typically, a smart valve can install on the utilities like sinks or radiators and/or the connection pipeline between the water supply network and the household plumbing network. The critical things of smart valve are the number of sensors. So that must be limited as much as possible to reduce cost and can enable the implementing in a householding context. So aim on this work is propose a smart valve that use only two sensors, a flow sensor and a pressure sensor. And this smart valve is able to detect leak both when the plumbing system is in use and when it's not. So our smart valve is posed on the pipeline connection between the water supply network and the house plumbing network, as I said before, two sensors, a flow sensor and a pressure sensor, and monitor online the system, both in case in in-use conditions, so when, for example, there is an utility open, or in stationary conditions, so no utility open. The leak detection system that we developed have three algorithms structured like this. So algorithm 1 is handle the stationary condition, meanwhile algorithm 2 and algorithm 3 in the in-use condition. But how we can understand if the system is in use? Simply see the data. So we acquire the data, both the flow and pressure data in buffers. There are first in, first out queues, and acquired with a fixed sampling time. And simply we check the last sample of flow measurements if then is greater than a flow threshold that near to 0 liter per minute. Then if yes, we are in use condition or else in stationary condition. In other words, we can say that in use condition, we have almost one opening utility. In stationary condition, all the utility percentage are 0. So let's start with algorithm 1. We use, in this case, only the flow measurements. And then we check the last measurements. And we robustify the algorithm using a simple auxiliary variable in order to detect if the flow is greater than 0 for an amount of time s. And then, if the flow is greater than 0, we arise the leak detection alarm. Otherwise, the non-leak detection alarm. Algorithm 1 considers a leak all flows between 0 and T0. So the tuning of T0 is critical in this case, and we in implementation phase that can be tuned as desired. So algorithm 2, algorithm 3 for the use condition shares two preliminary phases, the data acquisition phase and the data preprocessing phase. For the data acquisition phase, we acquire both the flow and pressure data. And if you consider the time instant T0 when a utility is open, we want to store the opening transient data. So we want to have R data before the open and NB minus R before T0, data before T0. These are is a parameter fixed implementation phase. The second step, once we have the data, is the pre-processing phase. There are two-step phases. The first step is a recursively square estimation, We assume an ARCS model where the Y is the flow measurements and the U is the pressure measurements, and we use the recursive least square with forgetting factor with the mu equal to 0.99. So the recursive least square gives us MB estimation of the two parameters, A1 and A2, called θ1 and θ2. So we store this MB estimation in two buffers, respectively B θ1 at and B θ at 2. Given this estimation, we simply mean the buffers to obtain the features Z, which is an array of two components. Given Z, let's see the core of algorithm 2. So simply, we redefine the Z, adding a 1 as a third component, and then we use a simple logistic regression model, where P is the probability of Z to belong on the class C, sigma is the sigmoid function evaluated in the argument of sigma, and J blue hat is the vector of the logistic regression parameters that are trained both on data from the healthy system and the faulty one by solving a maximum likelihood estimation problem. So the pseudocode is something like this. We simply check the probability of Z to belong to the class of leak, so the faulty one. And then if this probability is greater than 0.5, we arise the leak detection. The main problem of algorithm 2 is that require data from the faulty system, that in household plumbing system can be a tricky task. So we propose an alternative, algorithm 3, that use only LT data. Algorithm 1, given the feature Z, fit a multivariate Gaussian distribution on the LT network, and then where P is the probability and mu and sigma at are the parameters of the distribution trained on only data from the LT system. And then the structure is similar to algorithm 2. We check the probability. If it's lesser than the probability threshold close to 0, we arise the leak detection. So we test this algorithm on a real application. So we have a bench test that simulates a reproduction of a bathroom with two sinks and a shower, for example. And then this is the smart valve. And how we can do fault detection, we use a replaceable section of the pipeline. So that is a pipeline with the holes that allow to have a leak of 0.6 liter per minute or 1.2 liter per minute. The results, so we show only results for the in-use condition because algorithm 1 is very simple, so you can omit this. So the training phase of the logistic regression model shows that we obtain a linear boundary decision boundary. We perform a training phase on 27 tests. So for each utilities, we have 3 utilities. We perform 3 tests on LT system, 3 tests with 1.2 liter per minute, and 3 tests with a 0.6 liter per minute leak. A test is simply the opening of an utility from the completely closed condition to the completely open condition. The validation with 108 tests, which of them 72 are faulty tests. The confusion metrics show that this algorithm fails only misclassify only 5 tests that are false negative. We have an accuracy of about 95%. Algorithm 3, we train we fit the multivariate distribution only on 9 tests, so only 3 tests on the LT system for each utility. And then, with the same validation set, we obtain this result. Obviously, in this case, the the algorithm fails more. We are 19 in total misclassification, and an accuracy that dropped down to 82%, 82%. But comparing the two algorithms, the fault injection can be a very tricky task. So a loss of accuracy in algorithm 3 can be handled using more data for fitting better the distribution. So the conclusion, a little recap. Our smart valve has only two sensors, a flow sensor and a pressure one. We propose two algorithms, alternative from each other, to handle the in-use condition. One that needs the fault injection, that is algorithm 2, and one algorithm 3 that doesn't need fault injection. And then the smart valve is a real application. Thank you.
Thank you for the presentation. We have time for some questions.
Thank you. You talk about learning from the healthy system, right?
Mm-hmm.
But in practice, the system is not healthy, like in the case of distribution water systems, where the leak problems, the problem of leaks is an important problem. Like, for instance, in Acquedotto di Puglia, where I came from, it is stated that 50% of water is lost for leaking. So in that case, you don't have a healthy system to learn the model.
Yes.
Thank you.
But this application is thought for household applications. So the household plumbing system, typically, if it's new, is an healthy system. So it's not for a large scale leak detection. It's a consumer application that we can install in our houses.
Okay, thank you.
I have, what is a comment, another question. Do you assume a linear model when you have your linear at the beginning? This is not true.
Yes, but...
Even from laminar to turbulent flow, it could change a lot.
Yeah, we try to use this data-driven ANARCS model for the recursively square. We saw a distance between the features when the system is healthy and when the system is faulty, and so we try this way. We simply fit a linear model and we divide the two regions of the space.
The question is how small could be the leak? Because maybe a drop for a couple of hours, you don't detect, really you don't detect.
It depends from the sensor.
No, there are not sensors. The expensive sensor, that's 1% of the nominal flow, what you can recover. It means you cannot get better than this.
Yeah, it's a structural limitation. Okay, thank you.
Okay, are there any questions? If not, so let's thank the speaker again. So the next presentation will be given by Kuao Deng, and he will be talking about intelligent monitoring and optimal control of HVAC systems and its cloud edge implementation. So.
Hello, everyone. My name is Qiao Deng. I'm honored as a presenter our recent research on intelligent monitoring and optimal control HVAC systems and their cloud edge implementations. I'm from School of Automation at Central Southern University in Changsha. The first part is in introductions. The energy consumption of HVAC systems accounts for 30 and 14% of city total electric consumptions. HVAC systems frequently operate under fault conditions. Key equipment such as chillers, pumps, and cooling towers often function outside of its optimal range. So the health monitoring and optimal control of the HVAC system is of greater signification to reduce building energy consumption. There are three cycles in HVAC systems: chilled water cycles, refrigerator cycles, and cooling water cycles. The chilled water cycle remove the heat generated indoor and transfer it to the chilled water. The refrigerator cycle takes over transferring the heat from chilled water to the cooling water. Finally, the cooling water cycle releases the heat from outdoors through the cooling towers. The HVAC system comprises many components and is frequently changing operating modes, present significant challenges for health monitor and optimal control. These challenges include complex and variable operating modes and influence of multiple factors such as time and equipment and need of process and adaptive monitoring and control. In health monitoring, the existing methods include multivariable analysis methods such as PCA, CCA, and multilinear such as SVM and LSTM. However, they have limitations such as labeled day limited and parametric adaptations. In optimal control, the existing methods include rule-based methods such as expert systems, optimization algorithms such as reinforcement learning. However, they only focus on specific part of the system. In second part is health monitoring and optimal control method. The basic idea of CCA canonical correlation analysis is to find the close correlation between different parts of the system or different data sets. First, create multivariate sets U and Y. Then use CCA to get G, T, and sigma, and build a function called a residual generator to find faults. The goal is to find 3 key parameters by optimizing these functions. CCA's main purpose is to perform fault detection in real subspace U and Y. The overall framework just in-term learning CCA health monitoring method we proposed earlier include data collections, data processing, data clustering, real-time training, and real-time health monitor. In data collections, gather the historical and real-time data from the HVAC system. Then clean and standardize the data to remove the noise and outliers. Then cycle the historical data similar to the core data as the training data. Real-time training generated residual and construct statistic. Then monitoring the system health in real time and detect the fault as they happen. The overall framework of improved just in-term learning CCA health monitoring method as shown in this figure. The difference from the previous method is that the part of training data set update is added. Regularly update the training data set with new operating conditions to keep the method relevant. The hybrid particle swarm-based optimization control method involves several steps. Empirical model, list square fitting parameters, and set point optimization. This method uses the strength of particle swarm optimization to find the best operating parameters, improve the HV system overall efficiency. Developing energy consumption models for each component of HVAC systems based on historical data and system specifications, such as chillers, chiller pumps, and cooling pumps and cooling towers. Set point optimization, optimizing the set point of various control parameters to achieve the best performance. The target is mean total is the whole system energy consumptions. The development cloud-based platform allows for online verification and implementation of HVAC system monitoring and control method. This platform different from traditional platform because it enables real-time data processing and decision making. By using both the cloud and edge computing, we ensure the system working efficiently and effectively, even in the changing and complex environment. The third part is experimental study. The equipment and data set used in this experiment are provided by the real building in Nanshan District, Shenzhen, Guangdong Province. The structure of the HVAC system as shown in this figure. The improved just-in-term learning CCA method achieves better monitoring results than traditional method. This result shows that proposed method is very good at accurately detecting faults and minimizing false alarms. After optimization, the COP of the cooler cell system can reach over 5.7. The result shows significant energy saving and improved COP across different months. The cloud edge platform allows online verification and implementation of HVAC monitoring and control methods. This is different from traditional simulator-based and task-reg-based approaches because besides health monitoring and energy optimization, our platform upload some operational data in real time. Researchers can use this platform to upload their algorithms for real-time verification. And such verification is available at this. The last part is the summary. In this work, we proposed an improved just-in-term learning added canonical correlation analysis based health monitor method. Then hybrid particle swarm-based optimization control method to improve the energy efficiency of the HVAC system is proposed. Last, cloud edge platform is development for its implementation. That's all. Thank you for listening.
thank you for the presentation. We have quite some time for questions, if there are any. Okay, I might have one. So you mentioned that this is available, the verification is available at some site. So does it mean, does it run online, or is it just some history data and simulation experiments?
We upload some operational data in real time on this website. Our research can use this platform up their algorithm for real-time verification. There will give some indicator of the algorithm.
Okay, thank you.
Thank you.
Any other question? If not, please let's thank the speaker again.
Thank you.
We have some time, so maybe I would like to ask to upload the last presentation if it's not already there. The next presentation will be delivered by Arthur Liebert, okay, and he will be talking about CNN-based temperature dynamics approximation for burning rooms.
Exactly. Thank you very much. My name is Arthur Liebert. I'm a PhD student. My supervisor is Professor Niggemann, and I'm from Helmut Schmidt University from the beautiful place of Hamburg in Germany. And I'm working on ML approaches to make solutions for differential equations. And today's topic is convolutional network-based temperature dynamics approximation for burning rooms. And that what you see is that what you get. Let's start. Short summary. We start with the motivation. After that, we are facing some challenges. Then I will talk about how do we overcome these challenges. We look into an evaluation and one slide of key factors of the conclusion. Motivation. Close your eyes and just assume you are working on your favorite paper. And you like this paper so much, you light the candle to keep the ambience a little bit going. Suddenly the curtains caught on fire, the whole office building is burning down in a couple of minutes. Sounds familiar? I really hope not. So, could AI help in this extreme case of scenario? And my answer would be AI-based temperature prediction. What do we want to do? We want to take a temperature distribution inside of a room, and we want to make a prediction for the future, for the whole temperature distribution for the whole room. Not just one point in the room, every point in the room. Approximative. What are the challenges? Look at this beautiful monstrosity. This is the Navier-Stokes equation, and it's a partial differential equation that governs the conservation of mass, the conservation of momentum, and the conservation of energy for freely moving particles. And if we just could solve this thing perfectly, then we would have every temperature distribution on every place on Earth at every given time step. We would know how liquids would behave, how gases would behave. We would be done with research. Especially if you can prove mathematically that the existence of the solutions and the smoothness of those, or you find singularities, then you can go home with $1 million because it's a Millennium Prize problem. But for us, we don't want to solve this perfectly. We just want to make approximation for exactly those solutions. And I already hear you, but wait a minute, Mr. Liebert, aren't there already simulations that can numerically give us solutions to exactly that problem? You would be right. There are already solutions, but our problem is we have no real-time capability. In fact, if we simulate 1 second of a burning room, it takes us roughly 7 minutes of calculation time. And this would be 6 minutes and 59 seconds too late. The whole office building burned down once again. Another thing is, I know it's a running gag, but we just don't have real-world data. It's way too expensive. I already asked. The government won't let me burn down empty office buildings, but I think that was not quite a good idea anyway. Oh, sorry. So, another challenge is to get this video going. Okay, great. So, look at the next challenge. This is one two-dimensional slice of a three-dimensional solution. We want to have the whole three-dimensional solution, and we are just looking at the slice. And we see here already some challenges. Challenge 1, for example, would be there's a complex interdependency in the solution between temporal and spatial features. How can we process those interdependencies to make predictions? On the other hand, look how much pixel we have over here, and we have it in 3 dimensions. We have over 150,000 voxels that we need to calculate for one given time step. How can we reduce this complexity while still managing to have real-time capability and still managing not to lose too much information? That's another challenge right here. Maybe I can answer some of these challenges. How would I overcome them? So at first, we have a 4-phase model. Phase 1 is we need to overcome the lack of real-world data, so we have to simulate. We have computational fluid dynamics, and we use it. So we have 7 hours. It takes us 7 hours to calculate one whole experiment of 16 seconds of temperature distribution. We make use of it hundreds of times. After that, we have a pre-process. We need to reconstruct all the simulation data. We need to normalize it. We need to bring it into a form that we have naturally all those spatial and temporal features in it. Phase 3 would be the main part of the work. It's the proposed neural network, and finally it gets some training. The neural network I'll show you in one slide. The other thing would be, finally, we can make predictions, and here I want you to look into exactly this. You give me 4 tensors, and you get out 1 tensor. I know this kind of sounds like a scam, but hear me out. I need those 4 tensors. You could be so clever and just put sensors all over the place in one room, and you would get these temperature distributions for free. Those are past temperature distributions, and I would give you 1 distribution into the future. How would I do such things? Let's look at the main part of our work. We have the CNN 1D, 3D, that's our neural network architecture. And I know when mathematicians try to name things, they get really pragmatic. I have a one-dimensional encoding, I have a three-dimensional encoding. Let's call it 1D, 3D. Very clever. So, first challenge would be interdependencies. How do we face them? The interdependencies gets encoded right here. First, we have a temporal encoding. Secondly, we have a spatial encoding. So we encoded the already temporal encoded data and create a high dense latent space over here. Secondly, how did we overcome the challenge of the complexity? Right here. In the encoding process, we reduced the dimensionality of the time and the dimensionality of the spatial features, of the spatial dimensions inside of the tensors. We have a low dimension representation, but keep in mind, we need to counteract the loss of information. How do we do that? By just adapting the output channels in exactly that process. And then how do we manage to get real-time capability? We need to have as less calculations as possible. If you try to compare this whole construct that kind of looks similar to a unit with the unit itself, you will see that we don't have that much of in-between convolutions. We don't have a max pooling layer or average pooling layer that gives us the dimension reduction. We do all of the steps with one 3D convolution. That's what guarantees us real-time capability. And then we take the feature extracted tensors and apply a transposed convolution onto them, reconstruct the initial dimensions of the tensor, and get the prediction for one future time step right here and right now. Let's look at some results. Look at that graph. Okay, we have two graphs over here. Let me explain something. So this point is important. This is a crucial point. It's a point that lies inside of the fire. And you see already the blue line is the important line. That's the simulated temperature. That's the temperature we try to approximate, the real temperature. And we see there's high fluctuation, pretty intense to predict. On the other hand, we have a point that is far, far away from the fire, and we have much less chaotic behavior, but still it's not linear at all. And what we take away from this is we compare we compare the real temperature with a method that doesn't work with those interconnected spatial and temporal features. This would be the red line. It's just a neural network that just spatially tries to predict all of these room points. And then we try to compare this with our CNN 1D, 3D, our proposed method. And if we look into it, we see, maybe you don't see it that far away, but just trust me, the green line approximates the blue line much better than the red line, meaning our approach can hold up with all those crazy, chaotic movement. And keep in mind, we have over 600 degrees of changing in 1 second and such. On the other hand, what we can see is that our predictions tend to smooth the curve a little bit, which could be bad in some cases. In our cases, it's okay, because if we look into the future, we want to try to make predictions about material behavior. Maybe where will we get some cracks in the floor? Where will we have some outbursts or anything? And here, concrete isn't that sensitive over high fluctuations in short times, but more sensitive against average high temperatures. And that's the key point right here. A conclusion. What can we take away from this? Challenge versus result. Challenge versus overcome the challenge. We captured interdependency by applying temporal spatial encoding and decoding. reduce the complexity of the whole tensors. How did we do it? By decreasing the spatial dimensions, the temporal dimensions, and adapting the output channels. That's the crucial part. And we guaranteed a real-time capability by minimizing the number of calculations in the neural network by applying simple three-dimensional convolutions. Thank you very much for your attention.
Thank you for a nice presentation. When I was reading the title at the beginning, I thought, well, burning rooms, it's scary, but the presentation was nice. So we have time for questions.
Thank you for your effective presentation. I was wondering if you can embed some a priori information, like your Navier-Stokes equation, in a sort of physics-informed, so combining for sure data analysis in an effective way, but also with some physics rules in order to improve both the performance, but also to reduce the complexity, the time.
Great question. So we can't just use a simple physics-informed neural network. That would take way too long to get all those 150,000 points to predict. But what we can do is combine those things, and that's exactly the work that we are working right now. We try to combine exactly that with physics-informed. We take some differential equations, put it into the loss. We take a padding of the boundary condition, put it into the end of our neural network, and that's our a priori information that we try to apply right here. Yeah, thank you.
So, another question? Okay, I have one. It was really interesting for me that even in 60 seconds, the temperature can get pretty high.
Yeah.
So is it a standard room? The simulation of some standard room on office, or?
Yeah, there was no petrol inside of the room. It was a simple computation of a simple room, just one fire case. We had no furniture, no nothing. It was a pretty simple experiment, and it was getting that high. I was shocked as well.
Okay, yeah, it's really interesting. So, some other question? If not, let's thank the speaker again.
Thank you.
We are a little bit ahead of schedule, but I hope I will not make a lot of people angry when we continue directly. So the presentation will be about time series few-shot anomaly detection for HVAC systems. And please.
Thank you, everyone, for bearing with me to the very last presentation of the session. My name is Marcos Quinones-Guerrero, and this is joint work with my colleagues Yuxin Huang, Austin Corsi, and Gautam Biswas. And the title of this work is Time Series Few-Shot Anomaly Detection for HVAC Systems. So this is a very standard outline for the presentation. I'll be introducing the problem and motivation, then formulate it a little bit on the theoretical side, then describe the method, the approach we are proposing, go over the case study that we consider experiments and results, and came up to some conclusions. Let's start by the motivation, as discussed by a previous presentation in this very same session. HVACs are very heavy energy consumers in buildings, which is why it is extremely important to manage them very carefully, which is why detecting anomalies and faults very early in their lifetime is crucial for plant managers to make decisions so that energy is not wasted significantly. However, this is a non-trivial problem, and we are defining it into two parts. The first it is hard to detect anomalies. Why? Because buildings go through many different operating conditions, which can be very easily mistaken with anomalies. And the second one is that obtaining label data for a range of fault or anomalies is infeasible for most buildings. One solution for this is to reuse similar nominal data from other domains, and with other domains I mean it could be same building data from previous years, simulated data from similar buildings. Still, you face a big issue, and it is the issue of data curation, which takes a lot of time, because even in that past data there could be hidden anomalies that have to be identified. Therefore, even in this case, it is a non-trivial problem, and this is what basically motivates the idea of few-shot anomaly detection, which is basically, given this, that you have a model for anomaly detection that you have used for some time in the first place for one domain, how can you take advantage of that model, and with a little bit of data from a different building, you can fine-tune that model and see how it performs under those conditions. So to be precise, we are talking about a semi-supervised machine learning problem. Machine learning problems, you have standardly you have a supervised, semi-supervised, and unsupervised. And in the second case, you have a labeled normal or anomalous data in some particular cases. And for the target domain, which in this case will be the building for which we want to do anomaly detection, you might have a few labeled samples, let's say a few days. And of course, it has some limitations. You need to be very sure about the quality of the samples that you're using. But still, in terms of limitations, it is better than supervised, because for supervised, you require extensive label anomalous data, so you can train your classification model. And if you go fully unsupervised, then it's complicated, because there could be hidden anomalies in your anomalous data, in your nominal data that you have not identified. Therefore, we try to explore what happens if we try a semi-supervised few-shot methods, considering nominal instances from the source domain only, and a few nominal instances from the target domain. If we define that from machine learning perspective, it's basically a problem where you have a function that's basically trying to define whether an observation represents an anomaly or not. And what is the most proper architecture for that function, so that you can fine-tune it with very few examples for a target domain and still achieve good results in terms of anomaly detection. So the approach that we selected, it's a few-shot LSTM autoencoders. Well, one of the main issues, as I explained before, for HVAC systems is that they have multiple operating modes, right? So different approaches have been proposed to solve that problem. We ourselves proposed one approach where we use clustering techniques to isolate different operating modes and then create different decision functions, one for each cluster, and then combine them with some sort of Bayesian probabilistic method. However, in this case, we wanted to explore what happens if we account for the temporality of the variables. And for doing that, we can combine LSTM with autoencoders, which will try to capture both the temporal and the spatial relationships between the variables. So the steps for running this approach is basically 5. You, of course, have to pre-process your nominal examples. You'll train your LSTM autoencoders to reconstruct your data on your source domain. You'll fine-tune it with a few days for the target domain, define your threshold, and then use that for the rest of the observations. It's the standard methodology that we follow. To go a little bit into the architecture of the LSTM autoencoder, it's basically an autoencoder architecture that tries to learn a latent representation, but accounts for the temporality of the observations. To be more precise, accounts for the temporal relationships between the variables, which in cases of anomaly detection are crucial, because anomalies don't only reflect in the spatial relationships between the variables, but also in how they evolve through time. Now, the case study that we selected was developed by Lawrence Berkeley National Laboratory in the US, contains real and simulated data for an air handling unit in Iowa. contains 17 features captured every minute. And they actually impose some faults on the simulated data for both the real data and for the simulated. In total, it contains around 13 days for real data and 2 days for faulty data. And a crucial aspect of this data set is that the data comprises different days over a year to represent different weather conditions and different occupancy settings. The range of anomalies or faults that were simulated can be observed here to the right. They are mainly related to dampers getting stuck or valves being closed or open at a certain percentage, and some heating coil leaking. In terms of data preparation, we selected 11 nominal days as our source domain, as the real data. And in order to test how few-shot approach with the selected neural network architecture, we use different days from the nominal samples of the target domain. And in this particular case, a hyperparameter that you have to select is how many observations can capture the temporality. And we found through hyperparameter optimization that 10 was the best. Here on the right, you can see the final LSTM autoencoder architecture with some little tricks to prevent overfitting, like some dropout layers, and some of the hyperparameters that we found through a random search approach. Now let's talk a little bit about the results. Let's hope this figure is not too overwhelming. So here on the right, you have a comparison of the few-shot approach that we're presenting with 4 different settings, meaning that we use 1, 2, 3, and 4 days for fine-tuning. And we compare that with the other methodology that I mentioned before of clustering the different operating modes and then trying to learn a function for each one of them. And then when you have to combine the decision-making process, you can use either an Euclidean distance or a neural network itself. And so the area under the curve, as you may observe, the highest performance is obtained for the few-shot. However, that is not the whole story, because from a plant operations manager, the area under the curve is not the only important thing. So we have to consider the true positive rate and the false positive rate. And in that case, you can observe that there is an improvement by using the few-shot approach in the true positive rate. But there is a problem in terms of the false positive rate, which means that the number of alarms increase. As you, of course, add more days, you will see that the number of false alarms will decrease to a point where you have around 10% false alarm, which means that every 10 occasions that your system gives you an alarm, 1 of them will be false, which in many settings, in many environments, of course, is not acceptable. But at least the approach shows that this could be fine-tuned for certain specific faults, which could be critical for the system. Another thing that we did was analyze for each one of the faults in the system, and you can see as a general trend that the anomalies correctly detected, it means true positive rate, the few-shot approach improves over all the others, which means that tells us that capturing temporality of the variables, of the relationships, is extremely important to obtain good results with data-driven methods. Of course, there are still some possible research in the future. There are some faults which are very, very hard to detect, like the valve of the heating coil leaking at this specific setting. And this is because the anomaly behaviors are very similar to the nominal flow rate. But you can observe that for most of the faults, the few-shot approach works better than clustering. Besides, it's less labor-intensive because if you have to do clustering, and on top of that you have to do supervised machine learning, it takes a lot more time. It's much more time-consuming from a design standpoint. Well, and just to come to some of the conclusions, we tested few-shot anomaly detection for HVAC systems using LSTM autoencoders There are some strengths and limitations of our approach. The main limitation is the high false alarm rate given by nominal data for the target domain. And we think this can be solved by using some continual learning approaches to anomaly detection, which means that you, with time, will be able to assimilate that additional data as long as you identify that it is nominal. And from there, go and create this continual learning structure. These were the references used in the presentation, and don't hesitate to reach out either to the first author of the paper or to me. Thank you very much.
So thank you for the presentation, and we have plenty of time for questions.
Thanks, Marco. But one question, you lost me somewhere in between shortly only. You use the LSTM to create new labels for unlabeled data, but then you retrain for the next shot, right?
We use LSTM autoencoders to capture the temporal and spatial features of nominal data. And we fine-tune that architecture with 1 day or 2 days from the target domain, which means that it is a different building from the one that you use for training originally.
What's the shot for you? If you say it's a 1 shot, 2 shot, what defines one
1 day.
shot?
1 day of data, 2 days of data,
Okay.
3 days of data.
So
Sorry, I missed that part.
Okay, so you're not semi-supervised creating new labels, you're just using the autoencoder reconstruction capabilities to create an anomaly score.
Yes, that is correct.
Thanks.
Thank you.
Thank you very much for the nice presentation.
Thank you.
I'm wondering how flexible your approach is regarding, for example, the schema of the new building's data. So let's say I have a new building, but it records 10 sensors more or less. What would I do, and could I still apply your method?
Sorry, can you repeat the last part of the question?
So let's assume my new building has a different set of sensors, like 5 more or 5 less, or...
Oh, yes, that's a very good question. What happens if the new building has a different set of sensors? Well, in that case, my friend, unfortunately, you'll have to use a different kind of techniques, probably some data imputation. If that works, if the sensors are redundant, maybe there are some transformations that you could use to try to, try to impute the variables.
Thanks.
Sure.
Hello. Thank you for your presentation. It's very nice. You say at the last that you have a problem with the false alarms. And this is a big problem in the industry. And the alarm management is one topic that is really interesting for work. I am working in this topic of alarm management. Which type of techniques you are thinking working for solve this problem of analyze the false alarms? Maybe use some discrete event system for this, or I don't know, maybe what are you thinking for analyze this problem?
Yes, thank you. That's an excellent question. So for trying to reduce the number of false alarms, which in fact is a big problem in industry, there are a set of probabilistic techniques that we have used in the past, which basically we account for the temporality of the alarm and how it evolves with time. In this particular case, we keep the approach, let's say, pure, and we did not add anything on top of it. But very, very obviously, if we want to directly transfer this to a building manager operation, we will need to do some post-processing of the alarms generated by this approach. Still, we of course think that it is a balance, and so it depends on how you are able to detect the different faults, and in that case you have to be careful because there could be some faults which are more critical than other for the plan of managers, in which case you can sort of try to bias your detection thresholds to try to identify those faults more pronouncedly. Yeah. Thank you.
Okay, is there any other question? If not, let's the speaker, thanks the speaker again. So I would like to just thank all the authors, presenters, and you, our audience, for coming to the session, and it's closed. Thank you very much.
Hi.
Okay, I think that we can start. Shall we close the door or chiudiamo la porta? Okay, so we can start. I am Marcello Bonfè from the University of Ferrara, so I'm one of the organizers of this symposium. Welcome to the session, Cybersecurity and Cyber Attack Solutions. The first speaker is Chia Meng-Seng, so you can open your presentation. The title of the paper is Attack Isolation in a Water Treatment Plant.
So thank you very much for the nice introduction. And yes, good afternoon, everyone. My name is Meng Jia, and I come from the University of Kaiserslautern in Germany. And it is my pleasure today to present our work, attack isolation in a water treatment plant. So basically, we did a practical application of the existing fault diagnosis techniques on a real water system. So talking about the motivation of our work, so water systems, including the water treatment system, water distribution systems, are kind of critical infrastructures which heavily affect the human health and the environment. And also, due to the migration to cyber-physical systems, recent years for efficiency, we actually interconnect the network components with the physical components. And that's expose our system to the malicious entities. So therefore, unfortunately, water system has already been one of the top targets of the attackers, as there are up to 25 reported attacks in the US during 2015 alone. That is the reason why the attack detection of a water system has already attracted a lot of attention. And it is also very necessary to do the attack isolation after the attack has been detected, because we need to locate the attack quickly and accurately so that we can prevent the spreading of damage and also to obtain more attack information, which can be used later for creating some countermeasures. As mentioned, our work is based on a real plant called Secure Water Treatment Testbed, which can also be shortly called SWOT. So SWOT was launched by iTrust Center for Research in Cybersecurity, Singapore in 2015. It is dedicated to investigate cybersecurity of water systems, and it is a scaled-down real water system with 6 stages. A lot of work about attack detection has been done for SWOT, including the RCN graphic model, rule-based state condition graphs, and also the state observer and the recursive PCA. So luckily we can see that all of the attacks have been applied to this SWOT plant has already been able to be detected. And, but when it comes to the attack isolation, there is very limited work has been published, including Mr. Ahmed and Joe in 2021. They used a multi-model framework, which costs a lot of modeling efforts, and only a part of attacks are considered in their work. The reason is very simple, because besides variables that can be easily modeled, there are also a lot of variables, maybe from some very complex chemical reaction. It's very hard to determine their values, to model them, and also we have some actuator signals which have discrete values. So that's why we want to do the attack isolation in our work, we developed an attack isolation system for SWOT, and we tested using the real data collected from this plant. We, in order to isolate the attacks on the tank system to not just a range of components, but to a specific signal, we developed a novel model-based method. And also, there are some attacks on actuator signals. We try to develop a neural network-based method to isolate this kind of attacks. Before we go into details, I would like to first briefly introduce the plant, the SWOT process. So as can be seen that we have 6 stages, starting from the left top part. The raw water was supplied and transmitted through this pipeline where we have some chemical added into the water, some filters, and also the dechlorinator. And also we have some return water system and some water for the so-called backwash process in this process, so that the experiment can keep running. And it is worth noticing that these 3 tanks have water level sensors, while these 2 rest tanks have no water sensor levels. So in total, we have 51 monitoring variables, including 26 actuator signals, which are discrete valued, and also 25 continuous valued sensor signals. There are 2 real data sets collected from SWOT, provided by iTrust. The first one is the attack-free data, which recorded during 5 days and 18 hours. And also, very lucky we have the data set with 30 attacks, which has a real physical effect on the plant. It lasts for 5 days and 5 hours. The sampling period for both data sets is 1 second. So if we take a look into the SWOT attacks, there are 30 attacks that have been successfully launched to the plant. That means also there are some attacks they planned to be implemented, but they failed because of some practical aspects. And we have 13 attacks on actuators, 24 attacks on sensor readings. We have 20 attacks with single target, and also we have 10 attacks with multiple targets. There's no time overlapping between attacks. Now we try to design our our isolation system, and as we just showed, there are multiple types of variables and different types of attacks. That's why we design 3 isolation units to cope with different situations. The first one is called the dual observer-based attack isolation unit, which is used for the continuous value variables, and these variables can be easily modeled. In this case, these signals are the tank levels and the corresponding inlet-outlet flow rates. The next unit is the so-called reconstruction-based contribution isolation unit, and this one is also for the continuous value signals, but these signals are very hard to be modeled. And also for the attacks on the actuator signals, we have the neural network-based isolation unit, because we have a special situation here in the SWOT database that we don't have the recording of the control input signals. So let's first talk about the dual observer-based isolation unit. We extract the 3 tanks to build this tank system and show it in this figure. As can be seen, we have the water level sensors starting from LIT and the flow rate sensors starting from FIT. And the straightforward idea is that we can build up an observer to generate the residuals based on the difference between the measured water levels and the estimated water levels. That was fine, but the only problem is that if we look at the relation between the residuals and the possible attacks, it is not possible to uniquely isolate the attacks. So how can we address this issue? Our answer is that we further utilize the physical properties of the plant. There's a fact that the attacks that tamper with the water flow rates actually has much less effect on the estimated water level than the attacks that tamper with the water level. It is easy to imagine because there's always an upper limitation of the pipe capacities. And based on this fact, we come up with the idea that maybe we can develop the two observers with different gain matrices so that these two observers has different detection ranges. And as can be seen, we call these two observers fast observer and the slow observer. The slow observer is basically the same observer that we can see in the single observer scheme, while the fast observer is intentionally designed by placing its pulse so that it will be less sensitive to the attacks, so that it can only detect the attacks on the water level. And these are the state space function of the two observers. So how will it work? Let's check it with the real attacks. Here we have two successive attacks, attack 10 and attack 11, which try to change the values of the water flow rate, F8401. And as can be seen that for this slow observer, we have the third residual races due to the attack, and it triggers a line. So these attacks are detectable for the slow observer, but if we check the fast observer, there is no significant change on the residuals due to the attack, and thus these attacks are not detectable for the fast observers, and that is exactly what we want. So by introducing one additional observer, we actually have 3 more residuals, and we can obtain a new table of relation between residuals and possible attacks. As can be seen, for each specific attack, we can always find a unique combination of the residual signals. That means we can uniquely isolate all the attacks on the tank system by this unit. The next unit is the reconstruction-based contribution isolation unit. So this unit is applied for these variables that can very hard to be modeled. That's why we try to employ a data-driven approach called recursive principal component analysis. And we use this RPCA to calculate the combined index, use it for the attack detection. And to isolate the attacks, we employ the so-called contribution plot-based isolation algorithm, which will calculate the contribution of each variable to the combined index. And that will help us to determine which variables are actually cause the alarm. The advantage of this isolation scheme is that we can avoid smearing effect, which basically means the real reason of the attack is covered by the propagation of the attack. And also, RPCA can compensate the slow varying of the system parameter by online updating itself. The basic idea of the contribution plot-based isolation algorithm is shown here. I will not go into the details, but I want to use a small example to show it. So we're starting from 3 variables, x1, x2, x3, which are assumed as non-faulty at the very beginning. And bad news is that we already have a combined index, which is a dashed line, a bit larger than the threshold. So what we do here is that we will reconstruct x1, x2, x3 based on the rest variables, and we will use this reconstructed variable to calculate the new combined index, which is a solid line here. And we will find out, okay, by reconstructing which variable we can achieve the lowest combined index. In this iteration, we see, okay, it's x2. And we pick up x2, put it into the faulty set. We will keep doing that until the new calculated combined index goes back to the threshold. And finally, we will consider that all the variables in this faulty set to be under attack. The reconstruction equation is shown here. And let's check it in the real attacks. So here is the isolation performance of the attack 6 and attack 38. Here is the list of our variables used for RPCA, and this is the time axis. So we use different colors to indicate the contribution percentage of each variable to the combined index. As can be seen that for attack 6, The AIT202, it gives 100% of contribution to the index, while for attack 38, we have AIT402 and 502, these two variables share the contribution to the combined index. And if we compare this isolation result with the attack description from the document, we can see that this isolation result is correct. As we mentioned, there are also some attacks on the try to change the actuator signals. So here we analyze first this scheme. We use a typical man-in-the-middle attack scheme, where we can see that this is a part of the plant, and this is a controller. So the data exchange is realized by a network layer. So we also assume that we have a attacker here, which is able to change the values of the control input U and also the plant output and the actuator status. In the ideal case, we have U here, and this U will be changed by the actuator and received by the changed by the attacker and received by the actuator. And also we have the feedback of this actuator status. So that the easy way is that we can just simply compare this YC with U, and we can know that whether an attack was applied here, unless the attacker also changed this YC correspondingly. However, in this SWOT database, this U is not provided. That's why we come up with the idea that maybe we can establish a controller model to estimate U hat, and you use this U hat to compare with the feedback actuator signals, so that to detect and isolate the attacks. Because we still have the non-attack data set, and when there's no attack, we know that this U can be seen as equal to the feedback YC. That's why we can establish this model. Because the decision logic of the controller can be very complex, that's why we use a neural network for this purpose. We first got the inputs, including the 25 sensor signals and 26 actuator signals. We do the data wash, the data shuffling, and so on, and feed the data into the neural network. It is a fully connected neural network with 3 hidden layers, and for each hidden layer, we have 200 neurons. Okay, thank you. And the activation function is ReLU and linear. In conclusion, we can get the output of the neural network, which are actually floats. So, to get the estimated control input signals, we need to round these floats to the integers. Here we show the estimation performance of our neural network. We take the pump P203 as an example. This one is the output of the neural network, and this one is real control input. It can be seen that this is very well estimated. There's only a very short period of estimation error when these real control input U change. And we use it for the attack detection. For attack 70, it keeps the valve MV303 closed when it should be open. So we can see that at this time, the attack was launched. And at some point, we know that it's time to open the valve. But we know it because the NN output tells us that this one should be opened. But this one is somehow kept closed for some reason because of attacks. And that's why we got the residual and we detect the attack. And we know it's something, it has something to do with this valve MV303. So everything looks fine until one problem. We have some groups of highly correlated actuators in reality. That means these actuators, they share the same or opposite control input signals. For example, in this case, a very close pump and valve, they should be open together and closed together. And in that case, for these groups, we cannot say that, okay, this one is anomalies, but we cannot isolate the attack to this specific signal. Instead, we can only isolate it to this group. That means we achieve the partially isolated for these special actuators. And this is the overall isolation result. I will say it's very good because there are 25 attacks out of 30 attacks are uniquely isolated, and the rest 5 attacks are isolated to small groups of highly correlated actuators, as I just mentioned. So the conclusion is that we developed an attack isolation system for the SWOT process, and we tested on the real data set. The rest attack, the most of the attacks are uniquely isolated, and we developed a novel model-based attack isolation algorithm for the attacks on the tank system. And also to cope with the special condition that we don't have the control input signal, we use a neural network isolation method. And this study shows that the ability of fault diagnosis technology can not just detect the attack, but also to reveal the attack locations. Thank you.
No, wait, because we have time for one question. Sorry.
Thank you for your presentation, very nice. But I don't understand something because the analysis that you did in the plant, normally the instrumentation that have the plant is a bus, or for example, field bus or Profibus or something of this type of communication. When you talk about cyber attacks, it's from the website to the plant. Then the plant need to be connected to internet.
Yes.
Then you need in a firewall, you need something, strategies of cybersecurity for detect before you leave a door open. The hackers using that for improve. Maybe is very important in industrial processes for the people cannot attack. And I want to understand if the plan had all these all these barriers and the management of the network and encrypt the information, for example, as another technique, or put password or another thing. Many strategies for avoid the attacks of cyber attacks. I don't know if the hacker can pass all these barriers for attacking to one level. Let's say, for example, Siemens, Henderson Hauser, ABB, all this instrumentation is so how specialist for detect on this, and then maybe can you explain me why had too many attacks in their plant?
I hope I understand the question correctly. So it basically means that considering it's a study about cyber attacks, but what we see here is that someone going to the hardware change some signals, so instead of going from outside. Is that what you mean? Okay. So here, first thing is that this iTrust Center, maybe I didn't show it clearly, but these attack scenarios are really implemented through the network. So that is the first thing. The second thing is that, yes, for some actuator, for example, people can come and just keep it close. You can say it's not a cyber attack, but in this case, it's actually equivalent to our attack model, because we can see that here we have the control input calculated, and it's basically a signal that you say, for example, the valve should be closed, but someone here keep it open, so that's kind of equivalent. To me, it's equivalent to the, you have a target here that's to manipulate or change this control input signal to say, okay, don't close it. That's what I understand this problem. I hope this.
I have, yes, a very short question. Can you show slide number 16?
16, okay.
Yes, you achieved here a very wonderful fault isolation table, because all single faults are isolated. So distinguishability of faults is splendid. Have you applied any special design in the development phase of such a nice table?
Not yet. yeah, but we will consider it as future work. Thank you.
So this is a nice case, so to say.
Yeah,
You
it's a
still
nice
have
case.
to generalize the approach.
But I want to mention that we also did something on another water distribution plant also launched by the ITREST, and they do have a very similar scheme. That means we can easily use this, apply this method to the similar water systems. Yeah. Yeah.
Okay. Okay, thank you. Let's thank the speaker again.
Thank you.
Next speaker is actually the co-chair of the session, Michael Bartis, who is presenting the paper Modbus Vulnerability, How to Detect Sabotage Scenario. Okay. So that should be okay. Here.
I can.
Which one is this one?
This one. Okay.
Okay.
Presentation.
Okay. You should use the mic.
Okay. So I will be talking, my talk will be a little bit technical one, a little bit different than almost all of these that are presented in this symposium. So the topic is about the connectivity concerned with the Modbus, particular Modbus network, which is commonly used in the industrial practice. It is old-fashioned, I can say, field bus system, but still very, very popular in industry. And I will be talking how we can attack this Modbus network, particularly in the scope of any other approaches that are against attacks. So our session is devoted to the attacks and how to defend against these attacks. So my presentation was prepared by me and my student, and here's a little bit accent which is connected to Ferrara. So let us start. Why it doesn't work? It's off. It's on.
Use this button here.
Yes.
This one. There.
Okay. Okay. My eyes. Okay. I fault the eyes. It's a problem. So it's outlined. It's not very interesting in the moment because I will be going into my talk. So why? First, why hard to detect? I want to give some attacks that are very hard to detect. Why can we do? So the attack modifies frames. So it's very typically and very commonly used technique of sending in information in the networked system. So all CAN, Profibus, Foundation, Fieldbus, Modbus, and others. All the systems are sending information into frames. Frames are consisting typically from some fields. Fields are consisting from bytes or bits or mixtures of both. So the attack I propose modifies frames without compromising their formal integrity. It means that they are accepted as quite good in the sense of formal structure and content too. Wow. Is not this modifies phrase and formally correct and therefore are very difficult to detect. The attack is carried out in the real time. This is very important, not delays in the attack. I'm not sure that it works properly here, so sorry for shifting. The attacks are performed in a pseudo-random manner, so the attacks are not predictable, they are random, and therefore I think that they are a little bit difficult to detect. How it works and why Modbus? Because it's very widespread. But this recipe I propose is applicable not only for Modbus, but all the networks that are using are based on a special physical layer of our communication stack, which uses so-called RS485. It is used in Profibus DP of Profibus FMS2. The modification of this RS is used in CAN, so we can attack also the CAN Profibus as models as well. Here's only the example of a Modbus. The attacks I want to show, they are shown in. They are active, first of all. They rely on distortion of communications and modification of frames, very sophisticated. Maybe not very sophisticated, but the contents of frames are modified in such a manner that frames are not shortened, not extended, divided or something like that. Okay, so the fieldbus systems are everywhere in the process industry, of course, and here is a place where we can meet the fieldbus system, particularly the control system, or basic control system, is surrounded by the contemporary systems which are used in the process industry, and here is only this picture shows where we can attack. So here is only a few words about the typical explanation. Please excuse me for this is addressed for all the people who are not very close to the communication technology. More or less, the industrial systems are built from the levels, and on the lowest level they are so-called actuators and sensors, of course. They are connected to the control system and then supervising system. So the typical so-called bus topology is used in industrial field bus systems, and this topology has many branches. The most popular are buses, sometimes chains and trees, of course. So how works the Modbus? Modbus works in a very simple way. First of all, they are distinguished between two kinds of devices that are used. One of them is called a client. There's only one, and then the one, and then they are servers. And the communication between them is based on primarily on the Q and R. So the client typically sends a request or question to addressed device, and this device answers to the client. So I'm not sure it works. Oh. It works. So the communication is from the client to the server. Sometimes it's used so-called broadcasting, so the client is almost sending the information to all the network devices and nothing more, but this is probably most useful in the industrial practice. Maybe. Okay, so well, it's not working. Okay. I have troubles really with this pilot. Okay, so the stacks, the communication stacks between the devices which are connected by the network is shown over here, and the attacks I address are intended for a physical layer only. So my intention is to show the possibility of deliver a device, a physical one, which can be used particularly for the tests, not for attacks, because of ethics, of course, but if anybody wants, it can be also used for attacks for real networks. So there are two kinds of attacks. First, on the client frame, as shown here, or to the answer or response of the server. Very nice. So the sabotaging device, the implementation of the idea is in a sabotaging device, which can be connected directly to and in parallel to the bus. This device can be used for attack all the servers and even the client. But the experience is so that much more better is to attack not the client but the answer of a server. So the server can be for example, any sensor. It can be also an actuator too. So there are some. What's the idea behind this? As I said before, it's a hardware idea. So here is only the way how the 0 and 1s are typically transformed through the bus. So there are two lines. One is A and B, and 0 and 1 is depicted by the difference between the voltage across both lines. So 0 is -1 and B is, when the voltage is negative, the 0 is transmitted, in our case 1. So what would happen in the case of conflict? Conflict in the network is when at least two nodes or two devices are sending information at the same time. We have a conflict, and typically the networks are so designed that to avoid any conflicts. But if we make artificial conflict in the network, we can achieve a very nice feature, because we can see, I will skip maybe this slide because another one will. If we, for example, have two devices, X and Y, green and blue, and one of them is constantly sending 1 as binary 1 and second 0 and 1, the results on the bus is the copy of X. So the 1 does not conflict, does not comes into conflict. We can say it's a little bit recessive, so it's not so bad if one of them is constantly sending 1. Quite different situation we get. Oh, sorry. By 0, because the 0 is dominant. So it's like a very easy logic, Boolean logic. If you multiply, or if you make multiplication or a conjunction of 0 and 1, you get 0. So we can say, okay, the 0 dominates 1. Okay, and here is an example that exemplifies where we can attack the bits, and here is also an oscilloscope image that shows us that one of the bits here in this blue N can be cancelled by a conflict with a 0. This is this yellow line, okay? So in the real time, we can of course attack the frame. The most safe is to attack the last bits of last byte of so-called data field in the frame, but to get the feature that the attack is hidden or not visible to the devices in the network, we have also to check, to change something, the error. So a time which is devoted to first to calculate the possibility of attack is very narrow, but can be done. Here is an explanation how the attacks, first of all, the procedure is not very complicated one, and behind this is a little bit logic, but the logic is very, very simple at all. And two cases are typically considered first when the parity bit is used or not. This is technical information, more or less a realization of such a logical statements or functions typically very speedy and does not bring any problem when implementing. So I skipped these slides because and now here is typical student electronic mass. And two displays, which are typically used for washing station. And the program I will show is countdown to countdown. I show this in the film. I believe the film will be from the left side. You can see the countdown, and the second display is attacked. The attacks are very frequently, yes, they are coming in so-called bursts. Sometimes nothing, sometimes bursts, sometimes single attacks. And here we can see the attacks in a burst. Okay, so here are collected main features of such attacks. They are hardware-based. They are intended particularly for testing. Existing devices, existing networks can be easily used. Does not require any knowledge and a special commissioning and so on. They have, of course, a lot of advantages. Some of them are stated over, in particular, the big computational speed is required to make attacks in a real time. What's more, next will be in the future we will try to make sabotaging device in so-called serial connection, but it will be maybe next my talk about it. Thank you for your attention.
Any question? Yeah?
Thank you for your presentation, Professor. Very nice. I have one question in one slide. When you put the 7 layers of the OSI model, for the Modbus, where are the 7 layers? The physical layer, session, network layer, transport layer. Yes, yes. The international model of OSIs, the of 7 layer, is for any network. The TCP/IP is for the internet, that is more specific. But in the industrial process, I suppose that we don't have the network layer because no have IP address in the elements, and we don't have TCP and then I think that maybe this model is only the 1, 2, and 3, 4 layers.
Yes, right. For example, for Modbus system, by RS485, we use only 2 layers, typically of 3. Physical layer every time, because we use
we need connected to the...
And data link layer, of course, because we decode and decode the frame.
Yes.
And application layer as
it's okay. It's
okay.
on.
But
it's
a feature of ISO model, because we can use the layers of the stack as we want, because we can we can extend or we can move up and down the stack and reject the layers we do not want to use. And if you use, for example, IP and so on, we should go to the transport layer and network layer too. So in very simple industrial networks, they are really very simple and don't understandable for me, because the number of devices which are typically connected by the single network
local area network is small.
Very low, maybe 5, 10, 12, and so on. So they are LAN networks, very small one.
Okay. This is only the question.
It's not necessary to...
Yes. Thank you.
Okay, thank you. Any other questions? No? Okay, so let's thank the speaker again. I will leave the word to you, so if you want to present the next speaker.
Okay, thanks a lot. It's a little bit faulty, or I'm not very good. Okay, I have a pleasure to introduce the next speaker. It will be Emre Fayed, as I could read, and talk will be about Kullback-Leibler divergence-based tuning of Kalman filter for bias injection attacks in an artificial pancreas system. This floor is yours.
Where's the laser? The laser is this.
You can touch very.
Please use the mic.
I have troubles.
Good afternoon, everyone. I am delighted and excited to present our work to a global audience live for the first time. And the title of our paper is a bit mouthful, and chances are you are not familiar with one or more terms, and hopefully Kalman filter is not among them. Anyhow, sorry. So type 1 diabetes is a pandemic with increasing rates. I don't have the numbers here, but trust me, it's a serious problem. Otherwise, I wouldn't be paid for doing research on it. And if you are anything like me, you slept through your high school classes and you have no idea what pancreas does. It has multiple functionalities, but I will tell you one important functionality of it, namely it is responsible for blood regulation through the secretion of insulin and glucagon hormones. And unfortunately, patients who are affected by type 1 diabetes have a malfunction in pancreas, so they require external insulin administration to be able to survive. And the safe range for blood glucose levels are between 70 milligram to 180 milligram per deciliter. And if you're above that threshold, then you are facing long-term health complications. And if you're below that threshold, which is called hypoglycemia, you are facing short-term risks, which can even lead to a deadly coma. And in particular, management of type 1 diabetes is a tedious task, which requires frequent blood sampling, multiple daily insulin injections, carbohydrate counting, and whatnot. So, imagine we have this biomedical device which would automatically regulate blood glucose levels for those patients. Actually, you don't have to imagine it because it's a reality. Meet the artificial pancreas. It's basically a control system, single input, single output control system. We have the insulin pump as our actuator. we have glucose sensor, which is called continuous glucose monitor. They are all wearable devices. And then we have a control algorithm that will determine appropriate amount of insulin to be administered based on real-time sensor readings. And the communication typically happens over a wireless communication channel such as Bluetooth, and it comes with a risk of potential vulnerability cyber attacks if this communication is not well protected. And of course, traditional IT network securities should be there, such as encryption and message authentication, but they are never sufficient. So we propose to add additional secure of layerty through the lens of control theory. And in particular, we consider bias injection attacks on the glucose sensor. So a malicious attacker will try to drive the patient into hypoglycemia and danger the patient's life. And the challenge we address is that even though a bias injection sounds like a very simple attack scenario, it can be actually quite dangerous and hard to detect due to an integrator in the dynamics. And here in this figure, we are seeing this plot of detection probability as time progresses. And as time goes, as you can see, the detection probability seriously decays. So basically, the integrator kind of absorbs the bias injection. We propose what we call bias-sensitive Kalman filter, which would make this attack detectable for a longer duration of time and increase safety. All right, so we propose a model-based anomaly detection scheme, and it consists of two subsequent steps, namely residual generation and evaluation. I'm not going to spend too much time on this slide, given the audience expertise, but basically, I want to highlight that our focus will be on this part, residual generation. And now I'm going to talk about this information theoric metric, which is called the Kalbeck-Libler divergence. So it has this mathematical formula, but on the left-hand side and on the right-hand side, we have a nice illustration of it. So basically, it is a statistical distance between two distributions. The higher the KLD number is, the easier to tell apart these two random variables from one another. And it will be equal to 0 only when we have identical distributions. And in the context of secure control systems, KLD is used as a detector agnostic metric to measure the stealthiness of an attack. So in general, a higher KLD between the unattacked and attack residual means for the attacker reduced stealthiness. So the attacker will want to minimize KLD number to stay stealthy, whereas defender would like to maximize the KLD number to increase the detection rate. So it's, in a sense, a zero-sum game. Here is our problem setup. It's pretty standard LTI plant dynamics. So we consider an LTI filter as our residual generator, and our plant is subjected to stochastic but natural disturbances and a deterministic attack sequence. And we decompose the filter aerodynamics into two sources. One is due to natural stochastic disturbances, and the other one is due to the deterministic attack. And the derivation is quite straightforward. I'm just including this slide to get you used to the notation we use in our paper. Now this formulation was generic for any deterministic attack sequence, but we are going to analyze the special case of a bias injection. So if you replace attack sequence with the Heaviside step function, you can derive the following evaluation for the residual. And at time 0, the residual will be equal to 1, and then 1 minus CL, and so on. And if we have an integrator in the plant dynamics, then actually the residual will go to 0 as time goes to 0. So we formulate the attack detection problem as a statistical hypothesis problem. And for the null hypothesis, we assume there is no attack. So the measured residual is due to the stochastic disturbances, and it will follow this statistics. And when we have a bias injection, since it's a deterministic attack sequence, the covariance will remain the same, but it will have a time-varying mean, and this is reflected in the residual dynamics. So the question is, given this problem formulation, can we find an optimal filter gain which would maximize the KLD at all time instances? And the answer is unfortunately no. In particular, this is a multi-objective optimization problem, so we won't have a unique solution for all different objectives. So instead, we must pick a value, a time instant k, over which we want to maximize the KLD. And so let's select k is equal to 0. Basically, we want to maximize the attack KLD right at the attack onset. And if you do the math, actually, you will see that this is none other than the celebrated Kalman filter. So in our humble view, this is yet another interesting property of the Kalman filter. So it maximizes the KL divergence at the attack onset. And the question is Kalman filter then really the best for anomaly detection in this case? And the answer is no, otherwise there is no point to this paper. And in particular, Kalman filter is optimal during normal operation, but it will adapt too well to the compromised sensor readings in this case. So basically, it absorbs the bias injection too quickly. And our proposal is instead we maximize the KLD at the next time instant in order to slow down this decay rate and make the attack more detectable. So this is the formal formulation of our optimal filter design. We want to maximize this quantity overall stabilizing filter gains. And unfortunately, this is an intractable problem in general. But we propose a suboptimal solution based on Kalman filter tuning. So we select the filter sensor variance as the tuning variable. So the catch here is that we are not going to select the filter variance same as the actual sensor variance, but we are going to play with it as a tuning variable in order to maximize the objective function, KLD at time instance 1. So basically, we replace R with R prime in the Kalman filter equations, and this will be the corresponding Kalman gain. And in general, the filter covariance won't be equal to the actual covariance unless R prime is equal to R. And so we have efficient Lyapunov and Riccati equation solvers, and we can basically perform a grid search over this tuning variable to find the R prime value which would maximize our objective. And so in this slide, I present this part of residual evaluation part of our work. So we consider probably the most simple residual evaluator for stochastic systems, namely a stateless chi-square test, which would take the square of your residual and normalize it with covariance at each time instant. And we select the false alarm rate as 5%. And even though this may seem too simple, in our previous work, we have established an interesting optimal property of this test, namely it maximizes the instantaneous detection rate for a given false alarm rate. Now on to the numerical simulations. We consider a recent LTI model for blood glucose dynamics, which has also undergone clinical validation. And the sensor variance was 30 milligram per deciliter in this case. And in this plot, we play with R prime values from 0 to 200. And this is the KLD1 for the nominal Kalman filter. And this is the highest KLD number that we could achieve, which happened at this particular value. So after obtaining the gains for the nominal Kalman gain and bias-sensitive Kalman gain, we have calculated the detection probabilities for this particular attack scenario. So we have a step bias injection of 15 milligram per deciliter. And on the left-hand side, we have the KLD value as a function of time. And as you can see, at time is equal to 0, the nominal Kalman filter is indeed the optimal. But for the remaining times, the KLD number is higher for our proposed bias-sensitive Kalman filter. And the corresponding detection probability is what we are after eventually. And it follows a similar trend. But actually, this is already a really easy attack to detect. So instead, we consider a stealthy bias injection attack, where the attacker injects his bias in a slow manner using a low-pass filter. And once again, we have the same story, but I think the difference between our filter and Kalman filter is more dramatic in this case. And this is a sample trajectory from the Monte Carlo simulations. So on the right-hand side, you see this slow bias injection. And the blue curve denotes the blood glucose levels, whereas this dashed purple curve denotes the measured sensor values. And the attack injection starts at hour 1. And the hypoglycemia occurs around here. But we were able to detect the occurrence of hypoglycemia much earlier, and our filter was able to detect the anomaly even earlier than the Kalman filter. Yes, so I want to conclude my talk with possible future directions. In particular, we plan to investigate this KLD metric more in depth at different times and for systems with different sensor attack vulnerabilities other than this integrator bias injection vulnerability. And we also plan to investigate more smarter search algorithms such as bias gene optimization to design even better residual filters. That's it. Thanks for listening.
Yeah, I repeat. So thank you very much for your presentation. And if I understand you correctly, you use the KLD as a index, and you
as what?
An index. So
yes,
that you
exactly.
You design your Kalman filter in such a manner that you can maximize the KLD, and in that way you can also maximize the detectability of the attacks. But I saw there's always a trade-off between the detectability and also the false alarm.
That trade-off is a different trade-off than what we consider. So for any given level of false alarm rate, our filter will always outperform a Kalman filter.
So in this case, your given false alarm rate is 5%?
Yes.
I understand that the one who attacked this kind of system must be the worst guy in the world. So 5% is a little bit high. Do you think so? 5%?
Why would that be high, 5% false alarm rate? I mean, I can simulate it for also lower false alarm rate.
Yes.
And in that case, yes, the detection probability will reduce for both guys, but still our method will perform better.
Okay, yeah. Thank you.
Hello, thank you for your presentation, very nice. I have one question. You say that use or the sensor connect with the, I imagine, with the control system by Bluetooth. You say Bluetooth, yes? Bluetooth.
Sorry?
You say Bluetooth?
Bluetooth, yes.
Bluetooth, yes.
Yes.
Bluetooth is a kind of network point-to-point. Then it's so hard to hack a Bluetooth, maybe disturbance or something like that. I need to understand how, if the sensor is here and the controller is in the phone or is in, how is the hardware structure for this system? This is my question.
So you don't think that...
the sensor goes in the body, touching the skin.
Yes.
The sensor has Bluetooth or is connected with a cable to the system and the equipment, electronic equipment is connected by Bluetooth to the phone or to another where that is developed the algorithm of control?
There is no cables in this design. All the components communicate with each other via Bluetooth. We have only cable to inject insulin, but that's it's more like a pipe rather than a cable.
Okay. Thank you.
You have a question?
Thank you for the presentation. Just a curiosity, have you considered the presence of user disturbance like meal, carbohydrate, or physical activity during the attack or not?
Not in this work, but in our previous work, we addressed the problem of distinguishing sensor attacks from meal disturbances, because we can also apply model-based detection methodology since we have also nice physiological models for meal disturbances. But unfortunately, we didn't study the effect of exercise or physical stress since there doesn't exist good models for that. They are usually done by data-driven techniques, which I don't have the expertise. But yes, basically we studied those effects in a separate paper.
Yeah, thank you. And probably UAV Padova simulator are the possibility to simulate also physical activity.
Yes, so I don't use...
Just a comment.
Yeah. Okay, thank you.
Thank you. So let's thank the speaker again.
I have it's too late. Okay. So I invite the next speaker. Yes. Adaptive resilient control for a class of strict feedback your system under replay attacks. The attack will be held by Fanjing or he. It is, forgive my not best pronunciation of your name. The floor is yours.
Good afternoon, everyone. My name is He Wenjing. I'm from Beijing University of Chemical Technology. I'm delighted to have this opportunity today to share our work for you. The focus of my presentation about adaptive related control for class of street feedback, linear systems, and replay attack. I will divide my talk into 5 parts. First, let me introduce the background about our research. As we all know, each industrial revolution will bring major change in performance methods. The Industrial Revolution achieved the mechanization, and the industrial achieved acceleration, and the industrial 3 achieved automation and information. Also, now Industrial 4 will achieve intelligence and personalization. Also, the key systems of Industrial 4 is several physical systems, namely CPS. CPS are networked systems of human and devices that both sensor and actual change on a shared physical space for improved quality of life. Also now, many new infrastructure are integrated with information systems, such as smart city, smart grids, and intelligent transportation, and intelligent manufacturing. Also, the CPS face the threat of cyber attacks. In early stage, cyber intrusion and computer virus attack on cyberspace result in information systems faults. In such as worm virus, in third stage, the target attack on the sensing, decision making, and exclusion accept, causing operational faults in physical systems. Now, cyber attack became more and more intelligent. Also, cyber attack accompanying information attack and physical damage, leading to systemic pyramids of CPS, such as Virula breakouts and ransomware. So we can see that the cyber attacks have deleterious impacts on the production and life in the real world. Also, we can see excluding attack impacts and expanding attack surface and multi-security challenge and exposing clandestine attack methodology. So self-concern demand urgent attention. Also, cyber attack can be developed 3 types based on basic physical or network security. The first one, deception attack, destroys the integrity of information. Also, the denial service attack, DOSS, does the vulnerability of the information. This includes attack, destroy confidentiality of information. This paper focused on replay attack. Replay attack is as a deception attack, destroys the data integrity by repeating past message, which poses a major threat due to its ease of presentation and inherent difficulty in direction, as actors do not require knowledge of the system. Next, CPS faces 3 challenges. First, how to maintain acceptable personnel, and also how to simplify the control structure. Also, the research of resident control for CPS required reforms. Next, we will introduce the problem description. This paper focuses on adapt tracking control for class of linear systems suffering from replay attack in the sensor to control channel. Sorry, the equation 1 have a little trouble. Also, the systems mode of linear systems is shown on equation 1. The control objective of this paper is to propose a structure that to prove that all signals in control systems are bounded and the system out can bounded trick the desired signals. Also, the system's framework of this paper is shown on the right. Next, we will introduce a replay attack. The implementation process of case replay attack can be classified into the following 3 types. The attack eavesdrops and records the transformation date for a period of time. At the time of attack, the real and available transformation date is removed, and the story and the storage information is sent to receiver. Also, the duration and the delay time, of case replay task satisfy application 1. The key terms used in this paper we should introduce. The first one is adaptive control. Adaptive control is an effective method with little prior knowledge of system mode. Also, which aimed to reduce the impact of uncertainties on the stability of the control systems. Using the adaptive control, we can derive the adaptive control is by continuously updating the control law based on the data from the systems, thereby achieve the desired control objective. Also, the control, the control structure is showing this. Also, we know the uncertainty caused by jumping combination and the temporary data concerned with the advantage of adaptive control. So we use this in this paper. The next keyword is the mental dimensional Taylor network, namely MTN. MTN is a type of feedback network with 3 layers: input layer, and the middle layer, and the output layer. The structure of MTN is shown on below we gave. Oh, so sorry. I should use the PDF. The continuous linear functions defined a complete set can be estimated by MTN, which can express as equation 2. Also, we can know this one is the middle layer vector. This is the input layer vector, the high power term computed. So we can see this is the PMNS show. Also, the MTN have many advantages, such as simple structure, order ability, and real-time implementation. Next, let me introduce the main results. First, we introduce the transformation equation 3. Also, we consider some Lyapunov functions. The Lyapunov function Vz is used to prove the convergence of the Zg, and also the Vz is used to prove the boundedness of parallel error. Then we will use the implementing mathematical technology to scale the time derivative of Lyapunov function, thereby introduce the conservative of resulting stability analysis. Next, we will use the backstepping to design the adaptive control. First, we showed divorced the systems, knowledge systems, equation 1 into a number of subsystems. Also, then we will under press of stability of subsystems. We will virtual control signals will be derived type by type. Then the control signals U is finally designed. Also, finally, we got the control designed. So the pairs should make the following equation holds this one, and the control signals are updated by adaptive control law. Of this paper, the main result of this paper can be summarized as theorem 1. For the linear systems 1 and replay attack, if the concern is designed in the form of figures on the right, the adaptive law and the control signals. Then for any bounded in-room state, the control objective of this paper holds. Next, we will discuss the two cases of the system is and the replay attack. From equation 5, we will know in the in the bounce of replay attack, all the signals of the system is bounded. And also we can see equation 6 and equation 7 by integrating with them and using Hana equation, we will divorce that all the signals ZG and ZG is bounded. Next, we will introduce the simulation. The simulation uses a chemical reactor, which is used to verify the effectiveness of the control structure proposed. The mathematical model is shown on the 11. Also, we designed adaptive control, and it will be implemented on the system 11. And we consider the design signals as 12. Also, we consider the 5 replay attack on the sensor to control communication channel, and the start time, end time, and the delay time is shown on the following table. Next, we can see from figure 1 and figure 2, the satisfactory bounded tracking performance of the system 11 is achieved. We can see the system out, the systems out Y can track the decimal signals YD, but in the performance of replay attack, the tracking error can be increased, but it is bounded. Next, from figure 3.4 and 3 and figure 4, we can know that the control input and the state remain bounded all the time. Next, we will introduce the conclusions. Also, this paper is devoted to exploring for the MTN control of linear systems and replay attack, and developing an adaptive resilient control structure strategy. Also, a simple control is obtained. Also, we designed an adaptive law is to communicate the estimation error of the MTN. In the future, we will analyze the rest time required for the control performance to return to normal after a replay attack. That brings me to the end of my presentation. Thank you.
We are opening discussion.
Thank you for your presentation. I have a question. So you mentioned that you use MTN as a neural network for approximating the nonlinear part of the system, right?
Yeah.
So why you choose this kind of neural network? What is the advantage?
Oh yeah, I know. The mental dimensional Taylor network, right?
Yes.
Yeah. Also, we use it to deal with the linear functions, unknown dimension, linear functions. Or if we don't use, the main function of this OMT is to improve the transformation performance. Also, if we don't use this at all, we should deal with this unknown function in bounded term. So the devolved control should use the more energy to get the better performance. So, and also when we use the MTN, the estimation error can be reduced adaptively because we use adaptive control.
Do you compare with other neural networks?
Sorry?
Did you compare it with other neural networks?
Yeah, we tried. As we can see that MT can be considered as a neural network with special structure. With MT, they can obtain the similar results.
Okay, thank you.
Yes, thank you for your presentation. And that's my first time to hear about Taylor network, and that's my reason. And could you please explain the difference between Taylor network and conventional neural networks such as multilayer perceptrons or convolutional neural networks? What's their difference?
Oh, yeah, I get it.
Thank you.
As we can see, just now I just see that the MT can be considered as a neural network with a special structure. Because the difference means the middle level, as we can see. This one, the middle level is about input vectors high power of this. So, but the MT you use like RBF, so it is different. It's just the big difference between the MT and the neural network.
So it's like recurrent neural network, right? Recurrent neural network, RNN.
Yeah.
Okay, thank you. That's my question.
Thank you for your presentation. I have one question that I think that is a problem or a challenge in this field. When you say that there are an attack. Attack. Your model can detect a real failure in the system with an attack, because it's the same difference, then maybe can be misunderstood. This is a real failure in the system. It is not an attack, because an attack is for a third person outside of the process, yes? And failure is inside the process. Maybe your system can detect the difference between both?
You say repeat attack happens where?
When you say one attack is a cyber attack, that some people change the values or not, this attack type of attacks, or because
you
when they...
Sorry, wait a minute. This one?
No, when when you follow the signals and you time disturbance in the signal is when you say that here probably there are an attack. But maybe this is a possible failure in the system. Then how you can differentiate, is a real failure in the system or is an attack?
The attack will destroy the performance of the system, but they will make the tracking error is bounded, so it is sustainability also.
Yes, it's a control problem that you maintain the stability using the control system, but if the signal is contaminated, the algorithm is contaminated also too. Then it's the problem with that. But I think this is a challenge in the next researchers for detect if this is an attack or if it's a real failure. Thank you.
Yeah, thank you.
Okay, thanks. Yeah, question? On one very short question. Yes, what do you mean? There are some clever attacks. For example, the mixture of repeatability and denial of service and so on. Yes. Have you considered how behaves your approach in such a situation, situations where the different kinds of attacks are applied?
Oh, you just see this one? About this?
Okay, because you said us about the replay attacks.
Yeah,
It's,
replay attack.
It's only one kind of attacks.
Yeah.
They are a very wide family of different kinds of
Yeah,
attacks.
yeah.
And typically very clever attacks can choose the ways how they can be changed, and so the mixture of attacks, of different attacks, among them they can be used also replay attacks, but typically not now, because the attacks are more sophisticated than only one.
Oh, I know, I got
Okay.
you, I got you.
Okay.
We will analyze another attack. In the future work, I focused on the false data injection attack, FDI attack. But this paper not finished.
Okay, thank you.
Thank you.
Okay, good. Thank you. Thank you again. I'm asking if the author of the last paper, Daniel Osman, is here. You're here? Okay. So we are a little bit late, but you will have to put your presentation on the PC, right? It's already there? Ah, okay, sorry. Ah, okay, because it's no name there. Okay, so the next speaker is Su Liutao, right?
Yes.
So you can introduce the paper, right? Thank you.
Okay. Good afternoon, everyone. Welcome to my presentation. My name is Liu Taozhou. I'm a PhD candidate at the Institute of Automatic Control and Complex Systems from the University of Duisburg-Essen. My supervisor is Professor Stephen Dean. Today, I would like to present my work on the topic, an observer-based approach to mitigation of integrity cyber attacks. I plan to introduce my work in these 5 parts. At first, I'm going to introduce some background and motivations behind this study. Then some useful fundamentals will be presented. After that, I'm going to show you the main concept. Finally, some experimental results as well as conclusions will be made. Now, let's start with the first part, the introduction. In this study, we investigate cyber-physical systems. Cyber-physical systems incorporate control, communication, and computation. In general, they consist of 2 layers. Figure 1 is one schematic diagram of a CPS. It consists of a physical layer and a cyber layer. At the physical layer, usually we have our plant, actuators, and sensors, and or embedded controllers. At the cyber layer, we usually have some computational components, monitoring, and control units. This system configuration has many advantages. For example, it is a network control system. In the cyber layer, there usually exists sufficient computational resources and storage space. One challenge is that the data transmitted between the cyber layer and the physical layer may suffer from cyber attacks. Speaking of cyber attacks, they could be characterized into 3 classes. They are namely disclosure attack, for example, the eavesdropping attack, deception attack, for example, the false data injection attack, and disruption attack. Denial of service DOS attack is one of the well-known disruption attacks. In this study, we will only focus on this deception attack or the integrity attack. Now, let's make a quick review of the unified control and detection framework. This framework is proposed in this book. Initially, it is dedicated to fault detection and fault tolerance control. Figure 2 is an illustration of this framework. The centerpiece of this framework is actually an observer and observer-based residual generator. F is called the state feedback, Q is the Euler parameter, R is the one post filter, V is the pre-filter, G is our plant. This, each parameter in this framework has different functionality. For example, this state feedback F and this observer which is embedded in this observer will determine the nominal system stability. The Euler parameter Q can be tuned to improve the system robustness, fault tolerance, and disturbance rejection, and so on. This pulse filter can be used for the detection purpose, and this pre-filter V serves as a feed-forward controller. It can be optimized for reference tracking performance. As mentioned before, this framework is used to address the fault detection and fault tolerance control in a unified manner. As you may know, there exist some similarities between cyber attacks and physical faults. So one logical question would be, can we apply this unified framework for fault tolerance to attack resilience? To answer this question, this paper proposed another unified framework for attack resilience purpose. Here, I'm going to introduce this framework very briefly. In the next section, I'm going to explain it in details. In this framework, there are two sides, the plan side and the monitoring and control side. They correspond to the cyber and physical layer respectively. At the plan side, we have our plant G. The centerpiece of this framework is also an observer and observer-based residual generator. F is a local stabilizing controller. And at the MC side, we have one remote controller. This system configuration is promising in many aspects. Firstly, it has enhanced privacy. The overall controller as well as the residual generator used for attack detection are separately implemented at the plan side and the MC side. This resembles this multi-party computation for protecting system privacy. Secondly, it guarantees the fail-safe operation of our whole system. At the plan side, we have one local stabilizing controller. In this way, the system fail-safe operation and the nominal system stability can be guaranteed, even if the communication network is totally breaking down, for example, due to DOS attack. Lastly, at the MC side is usually realized based on the cloud platform with the aid of cloud computing sufficient some computational intensive control algorithms, for example, the data-driven methods can be used, thereby high control performance can be achieved. In this study, our starting point is the above system configuration. There are mainly three objectives in this study. The first one is to analyze the system stability and the control performance degradation in the presence of integrity cyber attacks. The next one is to synthesize a novel resilient controller to mitigate the influence induced by cyber attacks. The last one is to verify the proposed scheme in a network robot system. In this section, some useful fundamentals will be presented. In this study, we consider a linear time invariant plant model. Here it is with the following state space representation. We assume that the plant is controlled by an output feedback controller. Here, this K of Z is our output feedback controller, and V is our reference. It is well known that all stabilizing controller can be parameterized in the form of Euler parameterization. This is the left and the right co-parameterization of our feedback controller. This U, V, U hat, and V hat are the left and the right co-parameter pairs. Apart from the traditional realization of the Euler parameterization, there is an alternative observer-based realization. It is given by this equation. Here, this F is called the state feedback, X hat is the state estimation. It is obtained from the following full state observer. Qy is called the Euler parameter. Ry is the residual signal, which is generated from the full state observer. V bar is the filtered reference signal. The matrices F and L are chosen such as A plus BF and A minus LC are Schur matrices. In the following, I'm going to explain this framework in details. Our starting point is also this observer-based realization of Euler parameterization. As mentioned earlier, each parameter in this controller law has different functionality. For example, the F and this observer gain, which is embedded in this observer, will determine the nominal system stability. Remember that the system stability is a basic requirement of CPS. So in this way, we implement this stabilizing local controller here at the plant site. As mentioned earlier, this Qy can be tuned to improve the system robustness, fault tolerance, and the feed-forward controller here can be optimized for reference tracking performance. In this context, this orange part is implemented at the remote site. So in summary, at the plant side, we have one local controller. It is denoted as U0. It is one observer-based state feedback controller. Apart from that, the observer will generate the residual output residual RY as well as one input residual R0. It is equal to our real plant input minus the local controller. At the MC side, we will construct another controller. As proven in this paper, this residual signal can be used to detect attacks. As it will demonstrate later, we will use this residual signal in the design of a resilient controller. It is constructed based on the available residual signal as well as the received signal from the plant side. The remote controller C consists of two parts, the QY times RYA, then plus the filtered reference signal. In this study, we only consider the additive integrity attacks. For example, the transmitted residual signal from the plant side to the MC side, the RY and R0 will suffer from the additive integrity attacks, ARY and AR0. These are attacked reference residual signals. The generated input signal from the remote side will be transmitted to the plant side. This is the attacked remote control input. Finally, at the plant side, this is our real plant input. It consists of two parts, U0 and the attacked U1. And this feedback law, the closed loop dynamics is firstly examined. This is the feedback closed loop dynamics. This orange part is induced by the attacks in order to recover the performance degradation caused by attacks. This part should be minimized in the sense of a signal norm. Specifically, if you would like to mitigate this ARY, we could tune this QY. If this H infinite norm of this QY is sufficiently small, then we could say, okay, the influence of this attack ARY is minimized. The only problem is AU1, the attack signal in the input channel. As we can see, if the state feedback controller, which is embedded in the red coupon pair of our system, is fixed, for example, through offline design, then there's no freedom to mitigate this AU1. To solve this problem, we propose one novel resilient controller. Here, we would like to present the novel resilient controller. Before we construct this controller, we would like to evaluate the residual signal which is available at the MC side. After simplification, this residual signal available at the MC side is equal to AU1 plus AR0. We could see it is a function of the attack signal in the input channel as well as the output channel. In this way, it could be interpreted as an attack estimate. Inspired by this, we modify our remote controller by integrating this residual signal through one filter QU. QU is one stable filter. It will be explored later to mitigate this attack signal in the input channel. And this novel resilient controller, we firstly examine the closed loop stability. It is summarized in the theorem 1. The feedback system with the plant G and the controller C is internally stable if and only if the transfer function, the inverse of identity matrix minus QU, belongs to RH infinity for stable QU. Now we would like to have a deep understanding from the control theoretical perspective. As mentioned before, we could rewrite our controller in the equivalent output feedback form. This is the reformulated controller. As we can see, this attack signal ARY and AU1 will not influence our feedback controller K of Z. Their influence is equivalent to modifying our reference signal V of Z into an attacked reference signal. Similarly, we could reformulate our novel resilient controller in the similar form. This is the reformulated one. As we can see, the attack signal will also not modify our feedback system of the feedback controller Q of Z. If we compare this controller before and after modification, we could see there's one design freedom in front of this the attack AU1 in the input channel, it is denoted as QU bar 1. This design freedom can be further explored to mitigate these attacks. Through compare these two controllers, the control theoretical interpretation of this novel resonant controller becomes clear. In essence, one stable prefilter, the inverse of the QU bar, is added to the left covalent pair of our controller. This redundancy in the controller configuration has no impact on our feedback controller QFZ, but the resulting filter, this QU bar, functions as a feed-forward controller. It can be used to reshape the closed response from attacks. It could be considered as one extension from the conventional Euler parameterization. Now we would like to discuss about the resilient control synthesis. To do so, we get the closed response and the normal resilient controller. To mitigate the attack signals, we have defined 3 attack sensitivity functions. They are namely TRY, TU1, and TR0. To mitigate AR1, we can minimize the H infinite norm of the weighted TR1 with respect to QY. To mitigate this AU1 and this AR0, we could minimize the H infinite norm of the weighted TU1 and TR0 with respect to QU bar. Now we would like to verify the proposed novel resilient controller on a network robot system. This is our networked robot system, and its discrete time state space model is given by these matrices. The system input and output are the set points for these 3 motors, and the outputs are robot horizontal, vertical, and angular velocities. In this study, we consider 2 scenarios. In the first scenario, the sinusoidal attacks is considered, while in the second one, the constant bias injection attack is considered. In order to illustrate the influence of each attack and each part of the resilient controller, we launch them separately. Specifically, at the time interval from 0 to 10 is the nominal system behavior. In the following 3 time periods, we launch 3 attacks. Starting from the 40 seconds, we launch our novel resilient controller. We could say at about 15 seconds, the nominal output trajectory can be recovered. This is also the same case for the second scenario. These results demonstrate the effectiveness of our proposed resilient controller. Now, I would like to make a conclusion of this work. In this study, we firstly investigated an observer-based unified control and detection framework for attack detection and resilient control. Then we analyzed the closed-loop stability as well as the control performance degradation in the presence of integrity cyberattacks. Finally, to provide more design freedoms, we have synthesized a novel resilient controller in order to mitigate the attacks in the input and output channels. As for our future work direction, simultaneous detection of physical force as well as integrity attacks with its fault tolerance control and attack resilient control will serve as one research direction. That's all my presentation. Yeah, thank you for your attention and your valuable time.
Thank you. We have time for one very quick question. Anyone? Yeah?
Yes.
I may thank you for your presentation, very nice. But I only may comment for all the assistants, because I know that the International Society of Automation and the International Electrotechnical Commission have a series of norms, the 62443, that is the norm for cybersecurity in industrial system. 5 years ago, we are all the list of norms for avoid this type of attack. Then it's important to review all this norm, because the probability that there exists an attack is so low if you apply all this norm for prevent this situation. Then maybe it's an interesting topic that I go to work in my university, but before applying this norm, how we can make more secure the system. But thank you for for the presentation.
Yeah, thank you for your remark.
I understood the comment. So, to improve the impact of such solutions. Okay. Okay, thank you. Let's thank the speaker again. Okay, thanks. And last is Daniel Lossmann with attack detection in cyber physical systems via null space-based filter design. So, you have the mic.
I think I have everything. Let's see. Yes, works.
Okay. Okay. No, it's down there. Yes. Okay.
Okay, first of all, thanks for those who stayed here that long. I guess everyone's hungry, so I will try to make up some time. Also, for those who made the program, probably Christina Verde, actually did a good job because the talk fits nicely into the last one, which was a little bit more method-based. Well, it's 6 o'clock, so it's time for a story, I guess. I sat down a couple of, let's say months ago with a friend of mine. He's working for a drone company. And he said, he was kind of upset, right? And he said, what's up? And he said, yeah, we had some problems with our drones. They were attacked. 2 of them crashed. Yeah, can I help? And he said, yeah, can you do attack detection, right? And I said, okay, let's make a joke to cheer him up. And I said, no, I can detect faults because we're working 20 years in fault detection. And apparently he said, no, I need attack detection. I said, yeah, but it's the same, right? So, I mean, there's a small caveat to it, but essentially, system dynamically is the same. Well, I did not convince him at that day, and we left. And actually, as I went home and I couldn't get it out of my mind, and I was looking to the literature, and what I found there are a lot of papers solving attack detection problems, but there's a limited number of papers on actually talking about the methods, right? Because for you, being smart people, being here SAFEPROCESS, it's clear when I have a common filter, Lüneburg observer, or H-infinity stuff, whatever, I can apply that to the attack detection problem as well as a fault detection problem. Shouldn't be that different. And then I had this déjà vu where I thought, okay, 20 years ago when I was still a motivated PhD student, there was a similar situation. We went together, so I'm an aerospace guy, we went to Airbus and they said, okay, how can we bridge this gap to do fault detection? And 20 years later, here we are, fault detectors are flying on our aircraft, right? So maybe it's time to actually talk about a little bit about the methods that if industry people actually look for methods they can apply and they, I don't know, Google cybersecurity methods, they actually find one because there is a gap between the understanding of, okay, they actually can apply fault detection methods. And this is where I'm coming from today. So I'm presenting you a method I've been working last 15 years, improve it numerically and stuff, just to solve a different problem today. Okay, so long story short, let's dive into this. Was the high-level motivation. The low-level motivation was, as I said, the drone problems. We have projects where we use drones for firefighting or want to use drones for firefighting, and they are prone to attacks. If you look at the classical drone control loop, you have your control system, you have an autopilot. Mostly you use GPS, you have remote control stuff. And the problem is you can solve attack problems by using high-end stuff, right? However, if you buy this drone, it's probably, I don't know, 50 euros, $50. It's probably not you're going to spend thousands of dollars to make your drone, your remote channel secure. Okay, so there's some gap in between there because all of these things are actually prone to attacks. And now we think probably a couple of years further where these drones going to fly all connected. So it will make things worse. Okay. Okay, so this is where I'm coming from, where I said, okay, let's try to apply our methods we use for fault detection, and let's see where the difference are for me in the aerospace industry. Okay, so I started from scratch, to be honest. I figured, okay, one main difference here is, although it's similar, right, to the fault detection problem, in fault detection we like to
only consider the plant, right? So we have sensor failures, actuator failures, but here we are now, and we have a complete different, no, not completely different, but a little bit of different setup. There could be attacks on the controller, there could be attacks on the reference signal, and here it's a little bit of a weird setup. This should indicate that you could have like an input from someone being far away of the physical system and introducing some kind of signal. And this guy is actually motivated by the talk with my friend who said, okay, somebody injected our remote control signal and actually flew away with the drone. So something probably which you don't like to have. Okay, so as I said, the literature focuses on solving problems. There's some improvement for methods, and there's a little bit of unawareness, I have the feeling, on the methods, right? Especially when it comes to the application side. So there's some some gap to bridge. Okay, so I sat down and said, okay, let's formulate the attack detection problem as we did with the faults and see what's different. Let's assume we have a general system P. We have some measurable outputs. We have disturbances. For our aircraft would be wind. And we have some attacks. Relating to your question, you could add faults here, which makes the thing worse, right? Because how can you distinguish faults and attacks? Completely different story, something for the future. So let's talk about the method, how we design our filters. It's a little bit different to an observer-based approach. You're putting your trust basically in the measurements, okay? So taking that systems, what you actually want to do is you want to somehow, for a linear system, design a filter Q, which processes everything you know, which is your output Y, your measurements, and your input, which comes from the control system, from whatever, okay? So design constraints are, you want to make that residual small if there's no attack, and you want to make it big if there's an attack, and the filter needs to be stable. So this, I would say, is a classical, let's call it attack detection problem, which needs to be solved whatever method you're using, right? So you need to solve that if you use a Kalman filter, Lüneburger observer, whatever. This kind of has to be ensured. Okay, we're going to derive our approach to solve that problem directly from that equation here. So we're simply going to take this guy and put it into here, and what we're going to end up, or what we are ending up, is this guy. We have the residual depending on all our inputs, okay? And then the next step is, what we want to have is, we want to have this residual being 0 for inputs, control inputs, for disturbances, and now if you would say, I have faults too, which I want to decouple, you can stuck them in here too. If it's solvable, that's another story. Okay, so this is the idea of this null space-based approach. I think this is around for 25 years. Eric Frisk, who is here today, kind of started out with this. When I was at the German Aerospace Center, we worked on some numerics, which we think it's better, but that's the idea of this decoupling approach. If you can determine this Q, which needs to be a left null space of this guy, you have solved the decoupling problem, and unfortunately you don't see the green here, but it's supposed to be green. Unfortunately, you need to check if your attack is still coupled with your residual, okay? So this is the very basic idea. Okay, let's go. So you can solve the problem when this rank condition is fulfilled. It basically says, right, your attack needs to have some kind of a different effect as your disturbances. If you would have faults, the faults would go in here. Obviously, you only can solve it when the faults also are distinguishable from your attack. Okay, solving this whole thing, basically compute the left null space, is a little bit numerically involved, right? You can go with a polynomial basis, you can go with a rational basis as we are doing. I'm not going into details because we want to go to the application in a minute. Okay, so the nice thing, tools are available. Eric Frisk has a toolbox. We have a toolbox. It's since half a year also available in Julia. So if you like Julia coding, you can play around now with Julia. Both toolboxes are fine. If you would like to have the link, just approach me and I'll give it to you. Okay, so I think This is now a little bit of a difference to the actual fault detection problem because, as I said, we have various attack points here. And obviously, here, this transfer matrices PU, PD, PA, I left generic, while in the fault detection problem, we immediately target the plant there, okay? Here we would say, if we have attacks on sensors and actuators, this is the classical fault detection problem. But if we need to consider an attack on a controller, however that might work, you would need to have a different transfer function, meaning that, okay, this PU here would simply be your control algorithm. And I think the most interesting one is actually this last one, where you actually need to target the whole closed loop, okay? Because then you need to take the closed loop system and plug it into your design algorithm. You still have the disturbances to decouple because they are there. We cannot do anything against that. And we take the reference to the output as our attack transfer matrix. Okay, so that is the theory. If you're interested in more, that's all in the paper. Let's go to the application. As I said, unfortunately, my friend said, you cannot have the drone, it's too expensive for your university. I said, okay, I'm gonna go with a classical example with this Parrot mini drone. I don't know, some of you might know it. I think it's pretty cheap. The nice thing is, at least from a modeling point of view, the models are there in Simulink, so if you have MATLAB, you can just load that and you have all the stuff with a very complex control system. And so, no modeling, that's what control engineers like, right? Because modeling is the hard part. Okay, so here are some parameters. Well, it's actually pretty small, so it's just 60 grams, okay? As I said, all the implementation is freely available. Of course, you have to buy the MATLAB license. Okay, here we implemented a very simple control system. Here you see some step responses. So these drones, well, they have 3 degrees of freedom, but for control design, they are actually fully decoupled in the 3 rotations and the vertical axis. So you can actually design 4 scissor loops, nothing special there. And then we said, okay, let's take a look at an attack just to see if the methods are working, if we get similar results as we would expect. Okay, first, when you talk about sensor faults, obviously you need to decouple the disturbances. In a drone case, it would be wind. So this is what you see here. They actually look pretty similar. You can think of them being 0. So we did the decoupling, although we had considered 4 different disturbances that worked fine. And then what you see is, this is the interesting part. This is the fault, sorry, I'm saying fault now, right? The attack to residual transfer, and you actually see you kind of have a high pass behavior. This is pretty bad, right? When you think about a sensor attack, because this is usually what an attacker would do. He would or she would inject a very slow signal to make your system run away, like we have seen talks yesterday. So, however, this is due to we are only using IMU measurements and the GPS, right? And what this result basically says is, it's a classical result in flight control or in navigation, that you need to back your sensors because you need this integration of the speeds to the position. And unfortunately, this integration is due to sensor drift, so you need to have something else. If you don't have something else, you are not able to estimate the wind, or in this case, the attack, right? So this is definitely not a good solution. However, for me, it was more like the algorithms still work, okay? So whatever I thought about it, it's okay. But for a realistic problem, if you want to equip the drone with an attack monitoring system, you need to do something smarter. And there are smarter ways, implement cameras and stuff. Okay. Then we thought, okay, let's take a look at the control system. As I said, there are 4 PID controllers in there, basically. So you have, I think, a 5th or 8th order control system, because you have the parasitic delay in the PID controllers. Nothing special there, because when you think of the control system, you don't have any disturbances acting on it, right? You have the wind, but the wind is actually contained in your measurement and in this signal of the controllers. You actually can decouple the wind pretty easily or implicitly, so that works. And here again, control to residual is basically 0, and you have some nice coupling. Yes, you can argue this is actually looking nasty because you don't have a high frequency roll-off. This is what the algorithms give you. In practice, you would add some low-pass filtering to not get these high-frequency excitations there. Again, promising results that everything worked. Some notes, though. When you implement, this is a classical monitoring approach in flight control, right? So you take your full control system, you implement it on a dissimilar hardware, and you get some monitoring, right? So you could say, okay, nothing new there. However, with that approach, we're actually decoupling us because we can select the dynamics freely of our filter. If I just add a model running in parallel, I'm constrained by the dynamics of this model. By smart solving this null space, we actually can decouple ourselves from that. And to be fair, what would be a controller attack be? As said, I'm not really an expert on attacking stuff. I'm more like detecting it. So you said, okay, I could envision you have some, I don't know, malware or virus installed in there. And obviously, if there's malware on this controller, it will also probably be on your detector, right? Because it's on the drone. So if that's really a case, you could think of some decentralized monitoring where you have the monitoring on ground. That opens other questions because you have, again, a channel which transfers signals. So for me, this was the lessons learned were here. Yes, we can apply the stuff we use in fault detection. However, there's some fine caveats we have to look at in the future. Sorry. And yeah, this is where we are now. We have now implemented, I didn't show you any time simulation. This is what's in the paper. When the paper was submitted, we actually had already done some time simulations where we tried it out in the nonlinear model. I think there is some backup slides, yes, where we flew some kind of trajectory with the drone in simulation. At the moment, my PhD student is putting it on a drone, and we'll see how it actually works. But that's for the future. Okay, again, thank you for staying, and yeah, I hope I made up some time.
Okay, so I don't know if there is any question. You still have the same comment as before, I guess. Yes?
So first of all, thank you for this connection between fault detection and attack detection. And I think you have a valid point that the main difference is that with respect to attack detection, there are more entry points. So can you go back to that slide where you show those entry points? Yeah, this is good. Yeah, this works fine. So I would say that the entry point for the reference error, it's a little bit redundant in the sense that if you have sensor attack and the reference attack, then it will automatically translate.
Yeah, I see your point from the block diagram. I think I didn't come up with a nice block diagram in a way. What I wanted to show is that this reference is generated decentralized from the physical system. So you basically have this guy here is not a wire. So this guy is like sending from the ground to the drone, right? So you can inject that signal while this is basically after your measurement is compared to this guy. If I really have this one, I actually can't take my control system alone. I can take a look at the input of my control system because I computed this E. So I know this E, right?
Okay, yes.
Because this is the measurement minus my command, but I don't know what's happened in between basically here and here.
Yeah, exactly.
So I give you the point that at some cases this is the same.
Okay.
Right? But at some point I need to take a look at the whole closed loop system, but in certain cases I might be able to just take a look on the controller itself.
Okay, thank you.
Okay, so thank you again.
Thank you.
And thank you for attending. The session is closed. And tonight there is the social dinner for those of you attending. The good news is that it's a 12-minute walk from here. So it's pretty close. It's on the Teatro Verdi, the former Verdi Theater, just for those. Okay, thank you.